Black holes don't just sit still, they grow. Silently, relentlessly, and often invisibly, they feed on stars, gas, dust, anything that dares to drift too close. Some are the quiet anchors of galaxies, others are raging engines that shape entire cosmic environments. And the more they consume, the stronger their pull becomes. Unlike stars or planets, black holes are more amorphous in structure, which leads to a deeply unsettling question. What stops one from growing so large that it swallows the entire universe? Could a black hole somewhere out there be on a path to cosmic domination? Or, wilder still, could the universe itself already be inside one? Let's explore the nature of black holes, how they form and feed, the strange types we've discovered, and what current science has to say about the endgame of their growth. The fabric tears, when space-time ceases to hold together. Imagine space and time as a fabric, soft, flexible, invisible, and all around us. This is the way physicists explain how gravity works, how planets move, how light travels. It's the gentle stage where everything in the universe plays out. But there are places where this fabric doesn't just stretch, it snaps. Black holes are the deep wounds in the structure of the universe. When physicists talk about space-time tearing, they don't mean an explosion or a shattering like glass. They mean that the mathematical structure we use to describe the universe stops making sense. The numbers go off the charts. Equations that should return answers give only infinities. Time, which normally flows like a river, hits a dead end. Space, which can usually be measured and mapped, falls apart. This is what lies at the core of a black hole, a point known as the singularity. It's a place where all our physics, everything Einstein taught us, fails. The gravitational pull becomes so strong, the density so high, that the known laws simply can't keep up. We can't predict what happens inside. The rules we rely on to understand reality just stop working. It's hard to describe how unsettling this is for physicists. Much of science is built on patterns, on cause and effect, on smooth transitions, on the idea that the universe is logical. Theories are tested with data, predictions made with formulas. But here, in the darkest corners of the cosmos, none of it applies. Einstein's theory of general relativity tells us that mass bends space-time. It's what keeps the Earth orbiting the Sun. It's what makes apples fall from trees. That idea has held up for over a century. But when you push it too far, when too much matter collapses into too small a space, it pushes back. It says, I can't go any further. If we can't understand the inside of a black hole, it means our picture of the universe is incomplete. Something crucial is missing. We know the laws that govern the very small, quantum mechanics. We know the laws that govern the very large, general relativity. But they don't play well together, and black holes are where they collide. We like to think the universe is knowable, that with enough effort we can understand anything, that the cosmos, for all its size and strangeness, is at least consistent. But a singularity says no. It says there are places where nature itself turns opaque, places where even light can't escape, and neither can truth. Black holes are no longer just strange ideas on paper. We've seen their shadows. We've heard their ripples in space-time through gravitational waves. We know they're real. And because they're real, their mysteries are not optional. We have to face them. In that way, the tear in the fabric is an invitation, daring us to find what lies beyond. It forces physicists to dream bigger, to imagine a deeper theory that can explain what happens when the current ones fall short. Maybe it's string theory. Maybe it's quantum gravity. Maybe it's something entirely new. But whatever it is, it will have to be a theory that can handle torn space, broken time, and the terrifying power of collapse. Beyond the textbooks, the exotic family tree of black holes. The simplest kind of black hole is called the Schwarzschild black hole. It was the first type ever discovered in theory, named after Karl Schwarzschild, a German physicist who found a solution to Einstein's equations during World War I. Imagine a black hole that doesn't spin and has no electric charge. It just sits there in space, completely still. That's a Schwarzschild black hole. This black hole has only one feature that matters: its mass. The more mass it has, the bigger its event horizon, the invisible boundary around it where escape becomes impossible. Even time, from the point of view of anything falling in, becomes twisted and warped. But outside that line, gravity still follows the normal rules, just stronger. Despite its simplicity, the Schwarzschild black hole is a good place to start. It's the model that scientists first used to explore the idea that space and time could break down. But most black holes in the real universe don't sit still. Stars spin, and when they collapse into black holes, they keep spinning. That leads us to the next kind, the Kerr black hole. Discovered by Roy Kerr in the 1960s, this black hole spins around its axis, sometimes at incredible speeds. This changes everything. The spin drags space-time around with it. It's like stirring a spoon through honey. The honey twists and swirls because of the motion of the spoon. Around a Kerr black hole, space itself begins to swirl. This creates a strange region outside the event horizon called the ergosphere. In this zone, nothing can stay still. Space-time is being dragged around so quickly that anything caught inside is forced to rotate with the black hole. It's not the event horizon yet. You can still escape if you work hard enough, but it's a zone of no rest. Even light has to move in the direction of the spin. Kerr black holes are important not just because they're more realistic, but because they offer strange new possibilities. In theory, it might be possible to extract energy from them. Some scientists have imagined using their spin to power future civilizations. Others have studied their strange interiors, where the singularity isn't a point, but a spinning ring. And while we don't yet know what lies beyond that ring, some equations suggest it might lead to another universe, or a shortcut through space. But not every black hole is defined just by mass and spin. There's another ingredient that can change things: electric charge. That brings us to the Reissner-Nordstrom black hole, named after two physicists who studied what would happen if a black hole held an electric charge. This type of black hole doesn't spin, but it does have a positive or negative charge, like a giant cosmic battery. In practice, it's unlikely that real black holes stay charged for long. Opposite charges in the universe would be drawn to them, and the black hole would quickly neutralize. Still, as a theoretical object, the Reissner-Nordstrom black hole is fascinating. Its electric charge creates a second horizon inside the first. Instead of a single point of no return, there are now layers, outer and inner horizons, like nesting spheres. Between these layers, space and time behave in even stranger ways. Time may reverse, directions may flip, and the usual path of falling inward might bend and twist in bizarre loops. Then, at the crossroads of all these ideas, we find the most complex member of this exotic family, the Kerr-Newman black hole. It spins, it holds charge, and it's massive. It combines everything, mass, spin, and electric force, into one swirling object. In a Kerr-Newman black hole, all the strange effects from the others come together. There's frame dragging from the spin. There's electric repulsion from the charge. There are nested horizons, like shells inside a cosmic onion. And at the center, still the singularity, but shaped and spun into something unlike anything else in physics. Most black holes we expect to find in space are of the Kerr variety. They form from stars that spin, and the spin doesn't vanish when the star collapses. Even the giant black hole at the center of our galaxy likely spins. We've seen evidence in how matter moves around it, how it glows, and how it shapes its environment. As for charged black holes, they're probably rare, if they exist at all. But we still study them because they show us what's possible. They push the math to its limits. They challenge us to think about what happens when gravity and electromagnetism collide in one place. If spin and charge can change the horizons, what does that mean for the information that falls in? Could energy escape? Could information survive? Physicists are still debating. Some think these black holes may be more than just prisons for matter. The differences between static and rotating black holes. In the early 1970s, a physicist named Roger Penrose proposed a process in which an object could enter the ergosphere, split in two, and send one part into the black hole while the other escapes with more energy than it had before. That might sound like magic, but it's actually basic physics. The spinning black hole loses a little of its own energy, which gets passed on to the escaping piece. This process, called the Penrose process, is possible only because of rotation. A Schwarzschild black hole doesn't offer any such gift. It pulls in everything and gives nothing back. A Kerr black hole can be mined, at least for a while. Each time energy is extracted, the black hole loses a tiny bit of its spin. Eventually, if enough energy is pulled away, it could become non-spinning. In that sense, even black holes have a kind of life cycle. The effects of rotation don't stop at the ergosphere. They reach farther into space. Around a Kerr black hole, orbits become more complex. Particles don't move in perfect circles anymore. Their paths can wobble, twist, and spiral in strange patterns. Time itself flows differently, depending on which direction you're moving. If you orbit in the direction of the spin, time slows less. Go against the spin, and time slows more. These differences might seem small far away, but near the event horizon, they become extreme. The inner structure is also different. In a Kerr black hole, the singularity becomes a spinning loop, not a dot. Non-spinning black holes tend to be more quiet. Matter falls in directly, and while it heats up and glows, the activity is simpler. But spinning black holes can create powerful effects. As matter falls toward them, it doesn't fall straight in. It forms a disk, a hot swirling ring of gas called an accretion disk. This disk spins at high speeds, creating friction and heat. In spinning black holes, this disk can be twisted by the black hole's own rotation. This twist can lead to enormous jets of particles shooting out from the poles of the black hole. These jets can stretch for thousands of light years. They carry energy across space, shaping the formation of stars and galaxies. Non-spinning black holes don't seem to create jets like this, at least not with the same power. The power of rotation doesn't just affect matter, it affects light. Around a Kerr black hole, light bends, loops, and sometimes gets caught in orbits. Photons, the particles of light, can spin around the black hole many times before escaping or falling in. This creates the strange, glowing rings we now see in telescope images. These light rings carry the fingerprint of rotation. Spinning black holes are also more stable in certain ways. When two black holes collide and merge, the result is usually a spinning black hole. The leftover spin from both original black holes gets combined into one. These events send ripples through space, gravitational waves that we can detect. The shape of those waves tells us whether the black hole spins. In fact, almost every black hole we've detected through gravitational waves has been spinning. So while Schwarzschild black holes are useful for learning the basics, it's the Kerr black holes that dominate the real universe. They're more common, more dynamic, and more mysterious. Their rotation brings new regions into existence and opens up the possibility of taking energy from a place where nothing should escape. Yet, for all their power, rotating black holes still share something with their non-spinning cousins. The event horizon remains the great divide. No matter how a black hole spins or what it carries, what lies past it is hidden from view. Event horizons, one-way doors. At first glance, the event horizon doesn't look special. If you floated just outside it, you might not notice anything unusual, at least not right away. You could still move around, shine a flashlight, even try to fly away. But step just a little closer and everything changes. That thin boundary becomes a one-way door. Once you cross it, you cannot go back. Not because of any wall or force pushing you down, but because the structure of space and time itself no longer allows you to turn around. Space itself begins to tilt inward like a funnel. At the event horizon, that tilt becomes so steep that every possible direction you could go, forward, backward, up, down, leads deeper into the black hole. It's not that you're being sucked in, it's that the very map of space is changing around you. It's like walking over the crest of a waterfall. Before the edge, you could paddle away. After it, even if you paddle as hard as you can, you're still going down. That's what the event horizon is. It's the point where space and time are both tilted so sharply inward that no path leads back out. From the moment you cross the event horizon, falling in becomes more than just your direction. It becomes your future. Inside the horizon, the singularity isn't just a place you're headed. It's a moment in time you cannot avoid. Just as tomorrow comes after today, the singularity comes after the moment you cross. You can't turn around and go back to yesterday, and you can't turn around and get out of the black hole. It's now part of your timeline. That's the real difference between a black hole and something like a cave or tunnel. You can't send a rope in and pull someone back out. Once they cross the horizon, no message, no light, no signal of any kind can escape. Not because it's too dark or too far, but because the very rules of movement no longer allow it. Even if someone had the fastest rocket in the universe, they still couldn't make it back. They wouldn't even be able to slow their fall. Every second that passes only pulls them closer to the center. We're used to thinking in terms of speed. If something moves fast enough, it can escape gravity. That's how rockets leave Earth. They go faster than Earth's escape velocity. But at the event horizon, the escape velocity isn't just high, it's infinite. No speed, no matter how great, can get you back. And since light travels at the fastest possible speed, the fact that even light can't escape tells us that nothing else can either. That's also why the event horizon appears black. It's not because the black hole sucks in light like a vacuum cleaner. It's because any light that's trying to leave simply can't. It curves back inward or becomes trapped. From the outside, we never see what happens inside. We only see the outer shell, the horizon itself, and it looks like a perfect black circle in space. If someone were falling in, they would experience their own journey as quick and smooth. But for an observer far away, watching them fall, it would look like they're slowing down as they approach the horizon. Slower and slower, until they seem frozen right at the edge. They'd never appear to cross it at all. Their image would fade, redder and dimmer, eventually disappearing. But from the falling person's point of view, nothing strange happens at the horizon. There's no sudden bump or flash. They don't feel a shockwave or hear an alarm. They simply pass a point in space and continue on. There's no coming back, not even in theory. This is why physicists call the event horizon a causal boundary. It separates the universe into two parts, the part we can interact with and the part forever hidden. The inside is cut off from the outside, and that separation is absolute. What happens to the information that falls into a black hole? Is it gone forever? Does it stay frozen on the surface of the horizon, or is it destroyed at the singularity? For decades, this question has haunted physicists. Some say the information is truly lost. Others argue it's preserved in subtle ways we don't understand. This mystery has become one of the greatest puzzles in modern physics. Feeding the beast: how black holes grow over time. A black hole may begin as something small, maybe just a few times the mass of our Sun, but over time, it can become something much bigger, even millions or billions of times more massive. How does this happen? A black hole doesn't reach out and grab things with arms or claws. It doesn't need to. Its gravity is enough. If there's gas nearby, or dust, or pieces of broken stars, the black hole will start to pull that material in. The process begins slowly. A cloud of gas may be drifting near the center of a galaxy. As the cloud comes closer to the black hole, it feels the pull of gravity more and more. The gas doesn't fall straight in like water into a drain. Instead, it spirals inward. The reason is simple. Just like Earth orbits the Sun, gas and dust often carry a little spin. That spin keeps them from falling in directly and creates an accretion disk around the black hole. Accretion disks can be huge. Some are many times the size of our solar system. The material in them moves fast, close to the speed of light near the center. As it spirals inward, it bumps and rubs against itself. These collisions cause friction. That friction makes the gas heat up. And when things get hot, they glow. The inner part of the accretion disk can get incredibly hot, millions of degrees. At those temperatures, it gives off powerful radiation. Most of it comes out in the form of X-rays, though some parts glow in visible light as well. In fact, the light from an accretion disk can be so bright that it outshines everything else in the galaxy. When this happens, we call the black hole a quasar, or an active galactic nucleus. To someone watching from a great distance, it might look like the galaxy has a brilliant center, but the black hole itself stays invisible. The light isn't coming from it, it's coming from the gas that's about to fall in. Once the gas crosses the event horizon, it disappears. But before that moment, it shines with a brightness that can be seen from billions of light years away. This kind of feeding isn't always steady. Sometimes black holes go through quiet phases where little material is nearby. Then they're dark, silent, almost impossible to detect. At other times, something large, like a gas cloud or even a star, gets too close. Then the black hole comes to life again. When a star passes near a black hole, the outcome depends on how close it gets. If it stays far enough away, it may just swing around and keep going. But if it passes too close, the black hole's gravity stretches it like taffy. This is called tidal disruption. The star is pulled apart into a long stream of gas. Some of that gas escapes into space, but much of it falls into orbit, forming a temporary accretion disk. For a few weeks or months, the black hole flares with new light. Then it fades again. In the early universe, galaxies were full of gas. Black holes in those galaxies had more to feed on, so they grew fast. Over time, they grew into giants, supermassive black holes with millions or billions of times the mass of the Sun. Today we find these black holes at the centers of most galaxies, including our own. The one in the middle of the Milky Way is called Sagittarius A star, and it has about 4 million times the mass of the Sun. Even though it's huge, it's quiet now. There isn't much gas nearby for it to eat, but we've caught it flickering, sending out small flares of X-rays, little hints that it still has an appetite. As black holes feed, they also shape their surroundings. As gas spirals in and heats up, some of it gets pushed away. Magnetic fields and pressure can launch powerful jets of material into space. These jets shoot out from the poles of the black hole at nearly the speed of light. They can travel thousands of light years, blasting through the galaxy and beyond. These jets don't come from inside the black hole. They come from the area just outside the event horizon, where the forces are most intense. The jets carry energy far out into the galaxy. They can stir up clouds of gas, trigger new stars to form, or stop stars from forming by blowing gas away. In this way, feeding black holes don't just grow, they also act like engines, shaping the galaxies they live in. Feeding can be chaotic. Material doesn't always arrive in neat spirals. Sometimes galaxies collide. When that happens, huge clouds of gas are shaken loose. Some of it falls toward the centers of the merging galaxies. This sudden flood of new material wakes the black holes, setting off new bursts of growth and light. We've seen distant quasars that shine brighter than 1 trillion suns. Some of them got so big, so fast, that scientists still don't fully understand how they grew in time. It may be that feeding alone isn't always enough. That's where mergers come in. Every galaxy we see likely has a black hole at its heart. And that black hole has a history, a record of meals taken, matter swallowed, and energy released. Each one carries the story of what it consumed and what it left behind. Even now, we're just starting to grasp how important this feeding process is. Without it, galaxies might look very different. The stars might not form the same way. The light we see from deep space might not exist at all. Black holes feed with violence and grace. They glow with the heat of their meals. They blast jets into space. They leave marks on everything around them. And in doing so, they reveal that even the darkest objects in the universe have a kind of life. Black holes grow because the universe gives them fuel. Gas, dust, stars, all a part of their diet. And in return, black holes give back bursts of light, waves of energy, and the shaping hand of gravity. Cosmic cannibalism, when black holes devour each other. Sometimes black holes feed on each other. These are the rarest and most violent events in the known universe, two black holes colliding and merging into one. When this happens, the result is pure power. No light escapes from the collision, but space itself ripples like water struck by a rock, creating gravitational waves. For a long time, black hole mergers were something scientists only talked about in theory. They knew the math worked. They believed these events happened, especially in dense places like star clusters or the centers of galaxies. But no one had ever seen or heard one happen. That changed in 2015. In that year, a pair of detectors in the United States, part of an experiment called LIGO, recorded something new. The signal was faint and quick. It lasted less than half a second. But buried in that short blip was a story. Two black holes, each dozens of times more massive than the Sun, had spiraled into each other more than 1 billion light-years away. They had merged into one larger black hole, and in the process, they had sent out a wave of energy that stretched and squeezed space itself. That wave had finally reached Earth. These ripples, predicted by Einstein's theory of general relativity, had finally been detected directly. Since then, LIGO and its partner in Europe, Virgo, have recorded many more such events. Some of the black holes were small, others surprisingly large. In one case, two black holes crashed together to form a new one, with a mass around 150 times that of the Sun, a size that had never been confirmed before. In another case, a black hole and a neutron star collided. Each signal adds to a growing picture of how common and important these collisions are in the universe. Black hole mergers are different from the slower, quieter growth that happens when a black hole feeds on gas. This is not a gradual spiral inward. This is a violent final dance between two invisible giants. The two black holes may begin far apart, circling each other for millions or even billions of years. Each orbit brings them a tiny bit closer. As they move, they lose energy by sending out gravitational waves. Eventually, they get so close that they can no longer hold their separate shapes. They slam together and form one. During the final moments, the speed is incredible. The black holes can orbit each other many times per second. The space between them warps and bends. The energy released in those last seconds is more than all the light from all the stars in the visible universe. Yet none of it is light. It all goes into gravitational waves. The collision itself doesn't make a flash or explosion that we can see, so when black holes merge, we don't see the event. We hear it in a way, through those faint waves in space. Scientists turn these waves into sound, shifting them into a range we can hear. The result is a kind of chirp, a rising tone that ends in silence, as the two black holes become one. How do two black holes end up so close together in the first place? One idea is that they are born as a pair. Two giant stars may live together, explode, and leave behind two black holes. If they stay close enough, they may eventually spiral inward and merge. Another idea is that black holes may form separately and then come together in crowded places like star clusters or galactic centers, where gravity pushes them into tight orbits. Sometimes, scientists think that a merged black hole may get kicked out of its galaxy altogether. When two black holes merge, they can send out gravitational waves unevenly. This imbalance can give the new black hole a push, a recoil like the kick of a cannon. If the kick is strong enough, it can send the black hole flying away into space. Most of the time, though, the new black hole stays where it is and waits. Maybe another black hole will come close one day, and another collision will follow. Over time, this process may create the largest black holes we know. Gravitational waves carry information about the black hole's masses, their spins, and how far away they are. By measuring many events, scientists can learn how black holes form, how stars live and die, and even how fast the universe is expanding. Some black hole collisions may also help explain mysteries we still don't understand. For example, why are some black holes much larger than we expect from normal star deaths? Why do some black holes spin while others don't? And could there be other objects, strange ones we haven't yet discovered, hiding in the data? As detectors get more sensitive, we'll find more of these collisions. A new generation of observatories, both on Earth and in space, will allow us to listen to the universe with greater detail than ever before. We may even begin to detect black hole mergers from the early universe, when the first stars were forming. These events are rare for any one galaxy, but the universe is huge, filled with billions of galaxies. Somewhere, black holes are merging all the time. Every few minutes, one of these cosmic cannibal events happens out in the distant dark. And each time it does, a ripple in space begins to travel, moving at the speed of light, carrying a story from a time and place we will never see directly, but can still know. The Quiet Feast: How Dormant Black Holes Slowly Absorb Ambient Matter. Not all black holes shine or stir galaxies with storms of radiation. Some are quiet, so quiet in fact that they almost seem dead. These are dormant black holes. They're not at the centers of active galaxies, lighting up the universe with jets of energy. They don't have bright accretion disks blazing in X-rays. Instead, they sit in the dark, surrounded by emptiness, or what seems like emptiness. In truth, space is never completely empty. Even the regions between stars are filled with a thin soup of gas, mostly hydrogen. This gas is cold, low in pressure, and widely spread out. But it's still there, and over time a black hole pulls it in. This process is slow, much slower than the dramatic feeding frenzies of active black holes. The matter doesn't rush inward or glow as it falls. There's no clear edge to the action, no visible boundary between feeding and not feeding. Instead, the gas simply drifts toward the black hole under the pull of gravity, piece by piece, atom by atom. The key idea here is that black holes don't need to be active to be growing. As long as there's matter nearby, even in small amounts, the black hole will continue to absorb it. This includes single atoms of gas, rogue particles floating through space, even radiation itself in the form of photons that happen to wander too close. Once caught in the black hole's pull, these things cannot escape. Over years, centuries, and millions of years, the mass adds up. This type of feeding is often called Bondi accretion, named after the physicist Hermann Bondi. It describes the way that objects like black holes can slowly collect matter from a cloud of gas. There are no disks or jets in this case, just a steady inward flow from all directions. It's like a sponge soaking up water from the air. Gradual, quiet, almost invisible. Bondi accretion depends on a few simple factors. One is the density of the gas nearby. The more gas there is, the more the black hole can pull in. But in most parts of a galaxy, especially away from the center, gas is thin and cold. That makes the growth very slow. Another factor is the temperature of the gas. Hot gas resists falling in. It has more pressure and moves faster. Cold gas is easier to grab. So in cooler regions of space where particles move slowly, the black hole has an easier time collecting matter. Because of these limits, black holes that rely on this method don't gain mass very quickly. A black hole might grow by just a tiny fraction of its total mass over 1 billion years. But time is something black holes have in great supply. There's no rush. The Quiet Feast is about persistence, not speed. What makes this slow growth interesting is how it plays a background role in shaping the black hole's long-term history. After a major event, say the collapse of a star, or a merger between two black holes, what remains is often a black hole with little else around it. It doesn't stay that way forever. Over cosmic time, the surroundings refill. Stars drift by and leave trails of gas. Interstellar clouds pass nearby. Sometimes, the matter that's pulled in during this dormant phase is not evenly distributed. It may come in clumps. Small gas clouds, for instance, can wander close and get swallowed in chunks. These events are still quiet compared to major accretion episodes, but they cause tiny bumps in the black hole's growth. From Earth we may not notice them at all, unless a cloud gets close enough to heat up and emit a small flare of radiation before crossing the event horizon. In fact, the only way we usually detect these dormant black holes is by their indirect effects. For example, The motion of nearby stars may reveal that something massive and invisible is hiding in a particular part of the sky. A black hole might cause a star to wobble slightly or to follow a tight, fast orbit. This is how astronomers discovered the supermassive black hole at the center of our galaxy. Not by what it emits, but by how it pulls on the stars around it. Even stellar mass black holes can show up this way. In many cases, they're completely dark. But if they pass through a region of space with slightly denser gas, they may absorb enough matter to produce a faint X-ray signal. That's our only clue. This subtle, silent form of growth is a reminder that black holes are not always disruptive forces. When we picture them, we often imagine chaos, ripping stars apart, warping space, firing off high-energy jets. But the truth is, most of the time, most black holes are just sitting quietly, slowly absorbing what little the universe gives them. And even though this slow feeding may not seem important, over billions of years it adds up, especially for the black holes in the centers of galaxies, which can pass through different phases of activity. A black hole might be quiet now, but if conditions change, if a gas cloud falls in or a star wanders too close, it might awaken. The slow background feeding builds a kind of potential, setting the stage for what could become a sudden flare of activity. Why doesn't everything get sucked in? The limits of a black hole's appetite. Black holes are often imagined as giant cosmic vacuums, pulling in everything nearby with an unstoppable force. But in reality, space isn't full of matter rushing headfirst into these dark giants. Most black holes, even the supermassive ones at the centers of galaxies, are surrounded by space that seems quiet, almost empty. They don't pull in everything around them. In fact, most things nearby never fall in at all. There are boundaries, balances, and forces that hold matter in place. Black holes may be powerful, but their appetites are limited by the rules of physics. The first reason is motion. Just like Earth orbits the Sun without falling into it, stars and gas can orbit a black hole at safe distances. This happens because of angular momentum, a kind of motion that resists being pulled straight in. If a particle is moving sideways fast enough, gravity will curve its path into an orbit rather than a fall. And the faster or wider that orbit, the harder it is for gravity to change it. Angular momentum is a major barrier. Imagine trying to roll a coin into a funnel. If you aim it straight down, it might fall quickly. But if you give it a spin around the edge, it rolls in circles, slowly moving closer only if it loses energy. That's what matter does around black holes. It circles at a distance, often for millions of years, unless something robs it of speed or pushes it inward. Without that extra push or energy loss, it stays where it is. In fact, most of the stars that orbit close to black holes are stable. Even in the crowded core of a galaxy, where thousands of stars move quickly near a central supermassive black hole, very few are actually in danger of being swallowed. Their orbits may be wild and elliptical, but unless they come very close, within a small region called the loss cone, they simply loop around, unaffected. Gas behaves a little differently. It's lighter, more spread out, and more easily disturbed. It can clump together, drift inward, or get pushed around by other forces. But even here, not all gas ends up in the black hole. Some gas might be rotating fast enough to stay in orbit. Other parts may be blown away by radiation or stirred up by nearby stars. Just because gas is close doesn't mean it will fall. Another limit comes from radiation pressure. As mentioned, in accretion, disks matter heats up, glows, and gives off light. That light carries energy. Enough light in one direction can push matter away, like wind pushing against a sail. When a black hole is actively pulling in a lot of material, this outward push can grow strong enough to hold back new infalling matter. It's like a traffic jam. The light from inner regions slows down the inflow of outer gas. This process doesn't just happen in the most extreme cases like quasars. Even small black holes have a kind of feedback loop. As they pull in gas and begin to glow, they create pressure that pushes against further growth. The system tends to balance itself. In fact, this balance is one reason why black holes don't grow endlessly fast. they're limited by how much light they can give off without blowing away their own food supply. There's also the simple fact that most of space is empty. Even in galaxies, where stars are packed much closer together, the chances of anything directly hitting a black hole are still very small. A black hole, even one as massive as billions of suns, is still tiny compared to the distance between stars. And outside of galactic centers, space becomes even more sparse. The average density of matter in a galaxy isn't enough to constantly feed black holes. Sometimes galaxies can collide, gas clouds can be shaken up, stars can be flung inward, and black holes can suddenly find themselves surrounded by a feast. But this is rare on cosmic timescales. For millions of years between such events, a black hole might grow only a little, or not at all. A black hole's reach is determined by its gravitational pull, which drops off quickly with distance. Even though its influence technically extends forever, the strength of that pull gets weaker the farther you go. For a star orbiting far from the event horizon, the black hole's gravity isn't any more dangerous than the gravity of a star or a planet. Only inside a certain range, the so-called sphere of influence, does the black hole really control what happens. For supermassive black holes, this sphere of influence might be a few light years wide. For stellar mass black holes, it's much smaller. Beyond that, stars and gas follow their own orbits, guided by the gravity of the entire galaxy. The black hole becomes just one part of the larger environment, not a dominant force sucking in everything it sees. Even when something does get close, it has to be lined up just right. A star on a grazing path might get stretched by tides, but still survive the encounter. Only if the approach is deep enough will it be lost for good. And even then, much of its mass may be torn away beforehand, forming a bright flare before disappearing. In truth, black holes are picky eaters and often left in a kind of cosmic fast. Their gravity is immense, but it isn't magic. It follows the same rules that guide planets, stars, and everything else. For every force pulling inward, there's often a force pushing back, and for black holes, those counterforces define when and how they grow. The shadows that speak, how we measure the immeasurable. By their nature, black holes do not give off light, so how do you measure something that doesn't let you see it? How do you point to something invisible and say with certainty that it's really there? The answer begins with watching what black holes do to everything around them. Even though we can't see the black holes themselves, we can see their effects. Like wind-shaping trees or gravity-moving tides, a black hole's presence shows up in what it moves, what it bends, and what it heats. And over the years, scientists have developed tools to read those signs with growing precision. One of the clearest signs comes from stars. In the centers of galaxies, there are often stars that move in tight, fast orbits. Their speeds don't match the pull you'd expect from any visible object. Instead, they move as if something very massive is sitting nearby, something dark, something concentrated into a tiny space. By mapping those orbits over time, sometimes over decades, astronomers can calculate the mass of the unseen object that holds those stars in their grip. A famous example is the center of our own galaxy, the Milky Way. In the 1990s, astronomers began to track individual stars near a point called Sagittarius A star. Year after year, they followed those stars, taking pictures with infrared telescopes that could see through the dust in that region. What they saw was remarkable. One star, named S2, made a full orbit around an invisible center in just over 16 years. That meant it was incredibly close to something extremely heavy, about 4 million times the mass of the Sun. Yet no star or cluster could explain that mass packed into such a small space. The only explanation that made sense was a black hole. This method doesn't show the black hole itself, but it draws a sharp outline around where it must be. The precision of these measurements has grown over time, and today we can watch not just the positions, but the accelerations of these stars. They speed up as they fall closer and slow as they swing away. Every detail of that motion adds to our picture of the invisible mass they're orbiting. For more direct evidence, we turn to light. Specifically, how light behaves near the edge of a black hole. The Event Horizon Telescope, or EHT, is a global network of radio observatories working together to act like a single Earth-sized dish. Instead of collecting visible light, it gathers radio waves, which are better at seeing through dust and around sharp gravitational curves. By linking data from telescopes across continents and combining their signals through a process called interferometry, the EHT creates incredibly detailed images, measured in micro-arcseconds, tiny angles on the sky. In 2019, the EHT gave the world its first direct image of a black hole. It wasn't a photograph in the normal sense. What we saw was a ring of light, glowing gas swirling at nearly the speed of light, surrounding a dark center. That dark patch, the shadow, isn't the black hole itself, but the silhouette of its event horizon against the backdrop of hot matter. The shape of that ring, the size of the shadow, and the brightness pattern in the glow all matched what Einstein's equations predicted for a spinning black hole. It was like seeing a fingerprint, unique and exact for the first time. That image came from the center of a galaxy called M87, over 50 million light-years away. The black hole there is a giant, more than 6 billion times the mass of the Sun, and even at that size, its shadow on the sky was smaller than the width of a credit card seen from thousands of kilometers away. The precision needed to see it pushed the limits of technology, timing, and teamwork. Every telescope involved had to record petabytes of data, which were later shipped to central locations on hard drives for combining. There was no internet connection fast enough to do it live. But it worked, and in 2022, the EHT released a second image, this time of our own galaxy's black hole. Sagittarius A star is smaller and more chaotic, with gas moving quickly and changing shape in minutes. That made the imaging harder. But even there, the shadow stood out, a familiar dark shape surrounded by a glowing ring. Two black holes, two completely different galaxies, but the same physics at work. The size of the shadow depends on the mass of the black hole. The shape and brightness pattern depends on its rotation. And since those patterns are not just guesses, but follow strict predictions from general relativity, scientists can use the image to reverse engineer the black hole's features. Beyond imaging and star tracking, there's also the pull on gas and dust. Matter in the accretion disk gives off light that can be split into spectra, which carry fingerprints of motion, shifts in wavelength that reveal whether the material is moving toward us or away. This Doppler effect helps map out how gas flows near a black hole, how fast it spins, and how much energy it gives off. Even when the black hole itself remains hidden, the behavior of its disk becomes a stand-in for its identity. Sometimes, black holes announce themselves through sudden flares. These events give astronomers a short-lived but powerful way to measure the mass of the black hole behind the scene. How fast the light rises, how long it lasts, how the glow fades. These all carry clues about the size and pull of the black hole's gravity. In some cases, the dance is more subtle. Light from a distant galaxy or quasar may be bent around a black hole, creating multiple images or strange arcs. This gravitational lensing can reveal the mass of the black hole even when it doesn't shine. Like a glass lens bending light in a lab, the black hole acts as a cosmic magnifier, and the degree of that bending gives away the strength of its grip. Black holes may be invisible, but they leave a powerful mark, and each tool is like a different kind of radar, bouncing off reality to detect what can't be touched directly. Measuring the immeasurable may sound like a paradox, but in space, it's the everyday work of physics. By watching patiently, by building instruments that reach beyond our eyes, and by learning how to decode the signals in motion and light, we've begun to bring black holes out of theory and into clear, testable understanding. From stellar corpses to supermassive titans, a mass spectrum of darkness. Black holes come in a variety of sizes. At the smallest end of this scale are stellar mass black holes, which form when massive stars run out of fuel and collapse under their own gravity. Not every star will end this way. A star like our Sun, for example, will end as a white dwarf, a dense but stable object. A slightly heavier star might end up as a neutron star, a city-sized ball of tightly packed nuclear matter. But if the star is massive enough, typically more than about 20 to 25 times the mass of the Sun, its core can't stop the collapse. The result is a black hole. These stellar black holes usually range from about 5 to 20 solar masses. Some can grow larger than expected by colliding and merging with other black holes. Over time, this process can build up more massive objects. LIGO and Virgo have caught the ripples from these mergers, showing black holes forming with masses between 30 and 100 times that of the Sun. These events are short-lived and violent, but they leave behind something distinctly heavier. Above these are what some scientists call intermediate mass black holes. These sit in a strange middle ground. They're bigger than any single star could create on its own, but much smaller than the giants at the centers of galaxies. A black hole with a mass of, say, 1,000 solar masses doesn't fit easily into either of the main categories. Yet there are clues that such objects exist. Some come from dense star clusters, where stars are packed so tightly that collisions are common. Over time, repeated mergers between stars and black holes might form an object that grows large enough to qualify. Other evidence comes from ultraluminous X-ray sources, spots in the sky that shine brighter in X-rays than a single stellar black hole should be able to. If those sources are powered by black holes, they may be in this intermediate range, but confirming them is hard. They are rare, and they are distant. Unlike supermassive black holes, they don't anchor entire galaxies, so they don't have easy targets like fast-orbiting stars to help measure their mass. At the highest end of the scale are supermassive black holes. These are the giants, the monsters that sit in the hearts of galaxies. They can be millions or billions of times more massive than the Sun. The origin of these giants is still an open question. They are too big to have formed from single stars, or even from many merged stars. One idea is that they grew slowly, over billions of years, swallowing gas and merging with other black holes during galaxy collisions. Another idea is that some started out big, formed from the direct collapse of huge clouds of gas in the early universe, skipping the star stage entirely. If that happened, it would mean that supermassive black holes got a head start on their growth, giving them time to reach the enormous sizes we see today. Whatever their beginnings, supermassive black holes are closely tied to the galaxies around them. Observations show that the mass of a galaxy's central black hole seems to match the mass of its central bulge of stars. That suggests a feedback loop. As the black hole grows, it sends out energy that slows star formation in the surrounding region, and as stars form and die, they may help feed or limit the growth of the black hole. The two systems, black hole and galaxy, seem to evolve together. Even though they are so different in size, stellar and supermassive black holes share the same basic structure. They follow the same equations of general relativity. The differences are scale, not type. But that scale makes a difference in how they live, how they grow, and how we can detect them. For instance, in stellar black holes, the accretion disks get so hot they glow in X-rays. Around supermassive black holes, the temperature is lower, enough to shine brightly in visible and ultraviolet light. That's why quasars, which are powered by supermassive black holes, can outshine their entire host galaxies, not with X-rays, but with broad bands of light across the spectrum. In the future, astronomers hope to fill in the gaps of this mass spectrum. Better telescopes will search for intermediate mass black holes more carefully. More sensitive gravitational wave detectors will catch mergers from a wider range of sizes. Space-based observatories may reveal quiet giants that don't shine but still bend light around them. Every new detection adds another data point, another piece of the puzzle. Phoenix A, Ton 618, and other monsters lurking in the deep. Phoenix A is the black hole at the center of the Phoenix cluster. It isn't just large, it's so massive it challenged our understanding of how fast black holes can grow. The Phoenix cluster itself is one of the most luminous galaxy clusters in the observable universe. It sits about 5.7 billion light-years away, glowing in X-rays from its hot gas and pulsing with the energy of billions of stars. But deep in its heart lies something even more impressive, a supermassive black hole that, according to recent estimates, could weigh more than 100 billion times the mass of our Sun. Phoenix. A gained attention not just because of its size, but because of how active it still appears to be. Observations in radio waves and X-rays show that it's feeding, pulling in material from the dense surrounding gas and launching jets that stretch tens of thousands of light years. Those jets carve cavities in the hot gas of the cluster, giant bubbles that mark the black hole's presence even across cosmic distance. And yet, the gas around Phoenix A keeps falling inward. Somehow, even as it pushes out with energy, it still draws in more fuel. This balancing act is part of what allows it to keep growing, and part of what puzzles astronomers who thought feedback from a black hole this large would have shut down its own food supply. If Phoenix A is a surprise for how fast it grew, Ton 618 is a mystery from another angle, how early it appeared in cosmic time. This black hole lives at the center of a bright quasar, a blazing beacon powered by matter falling into its gravity well. It's located over 10 billion light-years away, meaning we see it as it was when the universe was only about 3 billion years old. And even then, it was already massive, estimated at more than 40 billion solar masses. That puts it among the top 5 heaviest black holes ever discovered. The light from Ton 618 is so bright that when it was first found in the 1950s during a survey of blue stars, no one guessed what it really was. Later, in the 1970s, it was identified as a quasar. It was the energy of that quasar, studied through its spectrum, that helped researchers estimate the black hole's mass. As more powerful telescopes improved our look at the early universe, Ton 618 became a kind of benchmark. If this black hole could grow so large so early, what does that say about the birth of the first supermassive black holes? What kind of seeds did they come from? And how quickly did they gather the material needed to reach these sizes? Other giants are scattered across the sky, each with its own story. In the galaxy Holm 15A, part of the galaxy cluster Abell 85, there's another record contender. Estimates put the central black hole of Holm 15A also at around 40 billion solar masses. What made this one unusual was the enormous faint core in the center of the galaxy, about 15,000 light-years across. That core is likely a sign of past mergers. When galaxies collide and their black holes spiral together, they often fling stars away from the center in the process. The more mergers that happen, the more stars get ejected, leaving behind a vast dim zone where the black hole dominates. The idea that black holes could grow to tens or even hundreds of billions of solar masses might have once seemed absurd. In the 20th century, some astronomers doubted supermassive black holes even existed. Now we not only know they do, we know some are far beyond what we ever guessed. They sit in ancient galaxies, in clusters so dense that interactions and feeding are constant. And we still don't have the full picture of how they got that way. Some researchers think there may be even bigger ones out there, yet unseen, hidden in galaxies where their surroundings are too bright or too chaotic to pick out the black hole's effects. Others wonder if the biggest black holes we see now are as large as nature allows. There may be upper limits. As a black hole grows, eventually its output will slow or stop the feeding process, keeping black holes from growing forever. But we don't know where that tipping point lies. We haven't yet seen the biggest possible black hole, if such a thing even exists. What we do see, though, is that they are found in galaxies that are unusually large, in clusters that are unusually dense, in corners of the universe where gravity has pulled together enormous amounts of matter. The upper limits. Is there a maximum size a black hole can reach? A feeding black hole's radiation pushback creates a natural balancing point, known as the Eddington limit. It's named after the British astrophysicist Arthur Eddington, who first proposed that for stars and, later, black holes, There's a limit to how fast you can grow by swallowing material. If the radiation pouring out becomes strong enough, it can blow away the very gas that's trying to fall in. For black holes, the Eddington limit sets a sort of speed cap. It doesn't stop growth entirely, but it makes it harder. Once a black hole is feeding near its Eddington rate, even a slight increase in the infalling matter produces so much radiation that the rest gets pushed away. Some black holes might grow faster than this under rare conditions. These are called super Eddington accretors, and they may play a role in the early universe, when dense clouds of gas were more common. But they're thought to be temporary. Most black holes return to the Eddington limit like a thermostat set by nature. A black hole that keeps growing at the Eddington rate will still get bigger, just slowly. Over billions of years, it might reach billions of solar masses. This seems to be how some of the largest black holes we've seen, like those in Phoenix A or Ton 618, may have formed. But if you give it long enough, could it just keep going? Could there be a black hole out there that weighs 1 trillion suns? This is where physics starts to push back with more than just radiation pressure. Another idea comes from the strange connection between black holes and entropy. In thermodynamics, entropy is a way to measure disorder, or more accurately, the number of ways a system can be arranged. Black holes, oddly enough, have entropy too. In fact, they have the most entropy of any known object of the same mass. The more massive a black hole is, the more entropy it holds. And there's a rule in physics, still unbroken, that says the total entropy of a closed system can't go down. This is sometimes called the second law of thermodynamics, and black holes follow it too. Here's where things get tricky. A black hole's entropy is tied to the area of its event horizon, not its volume. That means if you double the mass of a black hole, the area of the horizon and the entropy increases by a factor of 4. There are deep reasons for this, involving the strange quantum effects that seem to linger near a black hole's boundary. But if you try to cram too much matter into too small a region, the math stops making sense. It may be that there's a maximum entropy a single black hole can have without violating the rules that govern the universe. Some scientists have tried to figure out what this maximum could be. One approach looks at cosmological bounds, the size and energy of the universe as a whole. If a black hole becomes too massive, it can start to affect the structure of the entire space around it. For example, in certain models of the universe, if a single black hole held more mass than the entire cosmic horizon, the boundary beyond which light hasn't had time to reach us, it would break the rules of general relativity. That suggests a kind of upper boundary, tied not just to the black hole itself, but to the universe it lives in. Other models point to the idea that when black holes get too large, they start to resemble patches of the universe rather than objects inside it. In some speculative theories of cosmology, extremely large black holes might even create their own disconnected regions of space, like mini-universes branching off from our own. These ideas are still highly theoretical, but they hint at a deep connection between black holes, space, and the structure of everything. If there is a limit, it might not be just about mass, it might be about the nature of reality itself. When astronomers try to model how black holes grow through computer simulations, particularly in galaxy clusters, they find that feeding tends to slow down at high masses. This is partly because of feedback. This doesn't create a hard upper limit, but it does suggest a practical one. In this view, the biggest black holes we see might already be close to the natural ceiling. There are also limitations in the raw environment. The early universe had dense clouds of gas and frequent galaxy mergers, ideal conditions for rapid black hole growth. But today's universe is more settled. Galaxies still collide, but less often. Cold gas, the fuel black holes need, is less abundant in massive galaxies. That scarcity acts as another kind of limit. Then there's the question of time. The universe is only about 13.8 billion years old. That might sound like a lot, but for the slowest growing black holes, it's not nearly enough to reach absurd sizes. Even at the Eddington limit, growth takes patience. To grow from the size of a large star to billions of solar masses, you need at least 1 billion years. To go beyond that, you need even more. So far, the universe hasn't had enough time to let black holes reach their absolute maximum, if such a thing exists. Some researchers have tried to put numbers on the upper bound. Depending on the assumptions, the biggest black hole that could exist in the observable universe might weigh around 100 billion to 1 trillion solar masses. These aren't limits we've observed directly, but estimates based on how much matter is available, how fast black holes can grow, and what would happen if they went beyond that. If a trillion solar mass black hole exists, it would likely be found in a region of space far denser than any we've yet mapped. It's possible that black holes might merge enough times, in just the right sequence, to bypass the Eddington limit without needing to feed on gas. But even then, merging takes time. You need galaxies to crash into one another, then wait for the central black holes to find each other, orbit, and combine. Each merger adds mass, but it also adds years, millions of them. That slow clock means there's always a lag between how fast black holes want to grow and how fast the universe lets them. Despite everything we know, we've still only seen a tiny portion of what's out there. Newer telescopes, like the Vera Rubin Observatory and the James Webb Space Telescope, might help uncover more of these giants. And if one day we find a black hole weighing more than 1 trillion solar masses, it would force us to rethink all these limits. It would suggest there's something we're missing, some way nature found to sidestep the barriers we thought were unbreakable. Until then, the question of how big is too big remains open. If there is a cap on how large they can be, it's not just a limit on black holes, it's a message about the rules of the universe itself. Are supermassive black holes a composite object? As black holes grow, especially to extreme sizes, we're left to ask, are these truly single objects? Or could the giants at the hearts of galaxies be something else? Collections of smaller black holes, or even something stranger? At first glance, a supermassive black hole appears simple. But behind that simplicity lies a puzzling truth. We don't know what's inside. We can't directly observe the inner structure of a black hole, if it even has one. This leads to a fascinating idea. Perhaps a supermassive black hole isn't a smooth single-point object, but rather a composite system. One possibility is that the largest black holes might not be formed as one unified mass. Instead, they could be dense clusters of smaller black holes, packed together so tightly that their horizons overlap or merge into one apparent surface. What if, in certain conditions, black holes didn't fully merge, but rather became bound in stable, closely packed arrangements? In theory, a dense enough clump of black holes could mimic the behavior of a single, much larger one. From far away, all we would see is the combined gravitational influence of the system. Light would still be bent, nearby gas would still swirl into an accretion disk. To the tools we currently have, this would be indistinguishable from a supermassive black hole. But on the inside, it could be something more like a swarm, many smaller black holes dancing under shared gravity, their individual identities hidden behind the shared horizon. There are challenges to this idea. For one, black holes that orbit closely tend to merge over time due to the emission of gravitational waves. The waves carry away energy, causing the orbits to shrink. That's how stellar mass black holes eventually combine. In a dense black hole cluster, this process would still happen, perhaps even faster, because of the extreme environment. Over cosmic time, this would lead to a gradual collapse into a single object. So while a composite black hole might form temporarily, nature seems to push it toward unification. Still, the universe is big and time is long. It's possible there are stages during which a supermassive black hole isn't fully merged yet. These intermediate configurations, massive dark clusters of interacting black holes, might be rare, but they could exist. Another line of thinking comes not from clusters, but from the structure inside a single black hole. According to general relativity, a black hole has no internal structure in the usual sense. It's described entirely by just a few numbers: its mass, its spin, and its electric charge. This is part of what physicists call the no-hair theorem. But this view, while useful, may be too simple, especially for black holes that have grown to enormous sizes. At these extremes, quantum effects might matter. The math behind black holes starts to break down near the singularity. Quantum physics and general relativity don't agree on what happens there. This opens the door to speculation. Maybe, instead of a simple point, the core of a black hole has a more complex structure, especially if it has absorbed many smaller black holes over time. One idea suggests that remnants of smaller black holes, what some physicists call quantum cores, could survive inside the larger one. In this view, the interior of a supermassive black hole might not be uniform. It could contain layers or clumps of collapsed matter left behind from past mergers, each influencing the internal geometry. This doesn't mean there are planets or structures inside. It's still a place where matter is crushed beyond recognition. But in a mathematical sense, the curvature of space inside could reflect the black hole's complex history. Each merger might leave a kind of fingerprint, a distortion in the internal space-time structure that adds to the growing complexity of the whole. Some theories go even further, and in certain interpretations of general relativity, it's possible, at least on paper, that a black hole is not just a dead end, but a kind of bridge. If that were true, the internal structure would be unlike anything we've imagined. It might not just be composite in mass, but composite in connection, joined to something else beyond our universe or timeline. Our tools can't see inside a black hole. All we can do is watch from the outside. Yet even these surface-level clues might carry hints. If black holes are more than simple points, if their insides are structured in some subtle way, those structures could affect how gravitational waves form and fade. They might leave small anomalies, patterns in the data that don't fit the basic models. When LIGO detects a black hole merger, it records a kind of cosmic fingerprint, a pattern of waves that tells the story of the collision. Most of these match our predictions, but as detectors improve, scientists hope to spot tiny deviations, especially in the final moments when two horizons join into one. If there's something unusual inside, like leftover structures from older black holes, that difference could show up as a faint echo or an unexpected curve in the waveform. There's also the possibility that supermassive black holes formed in exotic ways from the start. Instead of growing slowly from stellar collapse, they may have begun as massive objects from the earliest moments of the universe. In this case, their interiors might carry imprints from the early universe itself, structures born not from stars and gas, but from the quantum chaos of creation. This question of what lies inside a supermassive black hole touches on deep physics. It ties together ideas about gravity, time, space, and the building blocks of matter. If black holes are more than just simple voids, if they have layers, histories, or composite parts, it would suggest that even the darkest places in the universe have stories written into their shape. The ancient ones. Supermassive black holes that shouldn't exist yet. Astronomers looking deep into the cosmos, so far that they are seeing light from over 13 billion years ago, have discovered something that doesn't seem to belong. Scattered among the soft glow of infant galaxies are brilliant points of light, shining with the power of 1 trillion suns. They're quasars, powered by black holes that, even in those early moments of cosmic history, had already grown into monsters. This is where the puzzle begins. These ancient black holes aren't just large, they're supermassive, and they appear in a part of the universe's timeline where, by all current models, they shouldn't exist yet. The universe at that point was less than 1 billion years old, still chaotic and rapidly changing. There hadn't been enough time, or so we thought, for black holes to grow that big. And yet, there they are. One of the most famous examples is a quasar called Ulus J 1342 plus 0928. It was discovered through a sky survey designed to find rare, distant objects. Its light took over 13 billion years to reach us, meaning we see it as it was when the universe was only about 690 million years old. That's incredibly early, barely 5% of the universe's current age. And yet, Even at that young age, the black hole powering this quasar had already reached around 800 million solar masses. Another, J0313-1806, discovered more recently, is even more massive and even older in cosmic terms, having reached 1.6 billion solar masses just 670 million years after the Big Bang. This discovery raised immediate questions. There's not enough time between the Big Bang and the appearance of these quasars for them to grow by accretion alone, unless they started off much, much larger than we expect. Direct collapse. Black holes could have skipped star formation entirely and collapsed straight into a black hole of perhaps 10,000 to 100,000 solar masses. That would give them a huge head start. But the early universe was a chaotic place. Forming such massive seeds required very specific conditions: low metallicity, strong ultraviolet backgrounds to prevent cooling, and regions isolated from early star formation. These aren't impossible, but they're thought to be rare. The number of ancient quasars we've observed suggests this process might need to be more common than our current simulations allow. In the crowded centers of the first galaxies, black holes might have collided more frequently than they do today. But even here, there are limits. Mergers can happen fast, but not instantly, and the larger the black holes get, the harder it is to bring them together, especially in a universe that hasn't had much time to build the kind of massive, gravitationally bound structures we see today. Still, another theory proposes that some of these black holes are primordial, that they formed directly from density fluctuations in the early universe, just moments after the Big Bang. These fluctuations could have collapsed into black holes before stars ever existed, meaning some black holes could be nearly as old as the universe itself. If true, this would allow black holes to start off much larger than previously thought, bypassing the problem of slow growth entirely. Some cosmological models even suggest that these primordial black holes could account for a portion of the dark matter in the universe. All of these possibilities are still being studied. None of them have been proven. The question is not just how big a black hole can be, but how fast it can get there. The existence of supermassive black holes so early in the universe suggests that something in our models is missing, or that nature found a shortcut we haven't fully grasped yet. The presence of these ancient giants also raises questions about the galaxies that hosted them. They were fed fast and grew aggressively. The galaxies around them were likely turbulent, full of collapsing gas and rapid star formation. The black holes may have shaped those galaxies even as they grew within them, regulating the rate at which stars could form by heating or pushing away the surrounding material. We are, in a way, looking back at a time when the rules might have been different. Maybe black holes grew faster in those early moments, through mechanisms we no longer see today. Or maybe our understanding of how black holes grow and how galaxies evolve needs a deeper revision. These ancient ones stand as quiet witnesses to a lost part of cosmic history. Seeds of darkness. Could primordial black holes be the key to early growth? In the very first fractions of a second, the universe expanded at an incredible speed. It was full of energy and chaos, filled with tiny fluctuations in temperature and density. Some of these fluctuations may have been just strong enough that the matter within them couldn't escape its own gravity. Instead of spreading out, it would have collapsed in on itself, forming a black hole right there in the early plasma, long before any stars had a chance to shine. According to Einstein's general relativity, if enough mass is squeezed into a small enough space, it must form a black hole. In the early universe, everything was already squeezed tightly. So if a region happened to be just a little denser than the rest, gravity could take over and trap it. These pockets of collapse might have created black holes with a wide range of masses, from something as small as a mountain to something heavier than 1,000 suns. Not all primordial black holes would have been large, though. Some theories suggest that they could have been incredibly small, less than a gram in mass, but still dense enough to be classified as black holes. These tiny ones would likely have evaporated quickly through a process called Hawking radiation. According to this theory, black holes aren't completely black. They slowly emit energy due to quantum effects near the event horizon. The smaller the black hole, the faster it evaporates. So most of the very tiny primordial black holes, if they ever existed, would be gone by now. But the larger ones, the ones heavy enough to survive for billions of years, could still be out there. Some might have merged over time, creating the first intermediate mass black holes. Others may have drifted into forming galaxies and sunk to the center, becoming the gravitational seed around which stars gathered. We know that dark matter exists because it exerts gravity, but it doesn't emit light, doesn't reflect it, and doesn't interact with normal matter in the way we expect. If primordial black holes were common enough, they could provide a natural explanation for dark matter's gravitational effects. They would be small, hard to see, but still massive, and there in the background, tugging gently on stars and galaxies alike. This idea has been tested in many ways, often indirectly. For example, astronomers look for microlensing events, where the gravity of a heavy passing object, like a black hole, briefly magnifies the light from a background star. If primordial black holes were floating freely through the galaxy in large numbers, they should cause microlensing from time to time. Surveys like Ogle and Macho have searched for these events. The results have been mixed. In some mass ranges, black holes of this kind seem to be ruled out as dark matter candidates, but in other ranges, particularly for black holes between the mass of the Moon and the Sun, the door is still open. Some researchers think that even if black holes don't make up all of dark matter, they might still make up a meaningful fraction. Maybe 1%, maybe 10%. That might not sound like much, but in a universe as massive as ours, even a tiny piece of the puzzle carries enormous weight. It would mean that some of the dark matter mystery is gravitational, not particle-based. That changes how we look for it, and how we think about the hidden side of the cosmos. Other experiments searching for primordial black holes have tried to find clues in the cosmic microwave background. If they existed in large numbers early on, their gravitational effects might have altered the way matter clumped together. That could have left subtle marks in the background radiation. Scientists have searched for these signs, and while no clear evidence has emerged yet, the idea continues to attract attention. Black holes, by their nature, are extreme. The early universe, too, was a place of extremes: heat, pressure, energy. It's not hard to imagine the two coming together. If these black holes formed just after the Big Bang, then they could carry with them information from a time we can't otherwise reach. They would be relics of the universe's first moments, preserved across billions of years. There are even more exotic theories. Some suggest that primordial black holes could have formed from the collapse of cosmic strings, thin, high-energy defects in the early universe predicted by some versions of string theory. Others suggest they could be connected to higher dimensions or undiscovered quantum gravity effects. For now, primordial black holes remain an open question. We haven't seen one directly. We can't prove they exist, but they offer a compelling way to solve several cosmic puzzles at once, from early black hole growth to the nature of dark matter. They don't require new physics, just a different way of applying the physics we already know to the chaotic conditions of the early universe. Why don't black holes swallow their galaxies? If black holes just kept eating, without any limits, they could eventually consume everything around them. In theory, a supermassive black hole could devour most of its host galaxy. And yet, we don't see that. We see galaxies with black holes that seem well behaved, not endlessly feeding, not swallowing stars wholesale. Instead, they eat in bursts and often go quiet for long periods. We've already discussed how radiation pressure factors into slowing down or even stopping the inflow of gas. That's one reason black holes don't just grow without end. But there's more. The jets that shoot out from some black holes are among the most violent phenomena in the universe. They can travel for thousands or even millions of light years, cutting through the galaxy and beyond. They carry away enormous amounts of energy, and they heat and stir the gas around the galaxy's center. When that happens, cold gas that might have fallen in to feed the black hole or formed new stars gets disrupted. Astronomers see the results of this in real galaxies. There are galaxies where star formation has shut down in the center, even though there's plenty of gas nearby. In some cases, it's clear that a jet from the central black hole has plowed through that gas, heating it up and making it less likely to collapse into new stars. The same jet may also have driven gas away from the galaxy altogether. Over time, this feedback changes the shape of the galaxy, the rate of star formation, and even the chemical mix of the stars that do form. Outflows play a role too. Not all the energy from a feeding black hole escapes in the form of jets. Some of it goes into winds, huge flows of gas moving outward from the accretion disk. These can be slow and steady or fast and violent, depending on the situation. They act like a pressure valve, removing material before it gets close enough to fall in. That not only limits how much the black hole can eat, but also changes the surroundings. These outflows can carry gas out of the inner galaxy and into intergalactic space. Over time, they may help stop the formation of new stars by making less raw material available. In some galaxies, especially smaller ones, the black hole may simply run out of food. If there's no cold gas near the center and no new gas falling in from outside, the black hole stays hungry. It may have grown rapidly in the past, but then hit a quiet phase. Without fuel, they fade into the background unless something stirs them awake. These self-regulating behaviors are some of the reasons black holes don't end up consuming their whole galaxies. Growth leads to feedback, and feedback limits growth. This balance is delicate, and not every galaxy follows the same path. Some galaxies can trigger sudden bursts of feeding that briefly overwhelm the feedback. But even then, the energy released catches up, and the black hole is forced to slow down. Intermediate mass. Black holes, the missing link or a myth? In the world of black holes, two types have long stood out: the stellar mass black holes and the supermassive black holes. Intermediate mass black holes, meanwhile, would fall somewhere between 100 and a few 100,000 solar masses. Dense star clusters packed with hundreds of thousands of stars, called globular clusters, orbit the edges of galaxies and are places where stars are packed close together and where collisions and mergers are more likely to happen. Some models predict that over time, a few massive stars in these clusters could sink toward the center, collide, and form a very large object. If it grows dense enough, it might collapse into a black hole, one too big to be stellar, but not big enough to be supermassive. Some globular clusters show odd behaviors that match this idea. Their cores move faster than expected, as if something massive is tugging at them from the inside. In a few cases, detailed studies of the star motions suggest a compact object of maybe a few thousand solar masses hiding at the center, but the measurements are difficult. Other explanations, like a crowd of regular black holes or neutron stars grouped together, can't be ruled out. So the evidence stays uncertain, like a blurred photo that hints but doesn't confirm. Another lead comes from unusual X-ray sources, called ultraluminous X-ray sources, or ULX. These are objects outside the centers of galaxies that shine much brighter in X-rays than stellar black holes should. For a while, astronomers thought ULXs might be intermediate mass black holes feeding at normal rates, too bright to be small. But later studies showed that some ULXs might just be stellar black holes feeding in unusual ways, pushing the limits of what was thought possible. Again, the evidence is mixed. Some ULX may still be good candidates, but no one can say for sure. Then came gravitational waves. In 2019, LIGO and Virgo detected a strange merger, two black holes, each much larger than usual, crashing together to form an object about 142 times the mass of the Sun. This final black hole, known as GW 190521, was the first strong case of a merger resulting in an intermediate mass black hole. It opened a new path to discovery. Gravitational waves don't care if black holes are feeding or glowing. They reveal mass directly. Now, With every new detection, astronomers are watching closely for more signs of these middleweight giants. If intermediate mass black holes really exist in large numbers, their presence would change how we think about the evolution of galaxies and black holes. For one, they could be the building blocks of supermassive black holes. Rather than growing slowly from stellar ones, which takes time and lots of fuel, maybe supermassive black holes formed more quickly by merging together clusters of intermediate ones. There's also the idea that these mid-sized black holes might play a role in shaping the dwarf galaxies that surround larger ones. These small galaxies often show signs of disruption and odd motion in their centers, as if something heavy and compact lurks inside. But again, proof is hard to come by. The galaxies are faint, the data is limited, and even with powerful telescopes, it's difficult to see what's going on at their cores. The next generation of space-based gravitational wave detectors, like LISA, will be able to detect mergers involving intermediate mass black holes much more easily and across longer distances. They might catch events that ground-based detectors miss, especially if they involve black holes orbiting each other over long periods of time before merging. Others are using precise measurements of stars near galactic centers to look for wandering black holes, those that might have been kicked out during galaxy mergers and now roam in the outskirts. If these objects bend the light from background stars just slightly or shift their position over time, it could reveal their presence. In computer simulations, intermediate mass black holes pop up all the time. They form in dense clusters. They sink to galactic centers. They merge with one another or get flung into space. The models predict them, but nature doesn't always follow the script. That's why each new piece of data, each possible sighting, draws so much attention. Some scientists have even suggested that intermediate mass black holes might hide in places we haven't thought to look, like the centers of faint gas-rich clouds or in the halos of galaxies where star formation never took off. These regions are cold, quiet, and mostly ignored in typical surveys. But they might be exactly where these mid-sized objects live. If confirmed, intermediate mass black holes would complete the mass spectrum. They would fill the strange gap between the common and the extreme. And they might give us new ways to understand the growth of cosmic structure and track the history of black hole formation across time. But for now, they remain a missing link. When galaxies merge, two galaxies drifting through space seldom stay forever apart. Gravity pulls on every star, every cloud, every dark matter halo. Over hundreds of millions of years, small tugs grow into full embraces. Spiral arms distort, tidal tails stretch, and eventually the two disks overlap in a slow, bright collision. Long before the final shapes settle, something else begins. Each galaxy's central black hole starts to feel the other's pull. What follows is a chain of events that can turn ordinary supermassive black holes into the heaviest objects the universe has yet made. When the outskirts of two galaxies first touch, the stars mostly pass one another unharmed. Interstellar gas, though, behaves differently. It shocks, heats, and piles up in great streams. Some of it is flung outward, lighting up as long, ragged plumes. Much of it, however, loses speed and tumbles toward the shared center. Those fresh flows of cold gas feed both black holes, which until now had been separated by tens of thousands of light years. Each black hole wakes up, switches on, and for a time the merging system can host two active galactic nuclei, twin beacons blazing inside a single chaotic envelope of stars. The orbits of the two black holes decay through a process called dynamical friction. Picture each black hole plowing through a sea of stars and dark matter. As it moves, it pulls some of those stars along. The collective gravity of that trailing wake acts like a brake. Slowly, step by step, the black holes spiral closer, shedding orbital energy into the surrounding galaxy. At a few thousand light-years apart, they are still distinct, but the shrinking continues. Tidal forces churn more gas inward. Bursts of star formation ignite, then snuff out when radiation and supernova winds blow the fuel away. By the time the separation falls to a few hundred light-years, astronomers begin to call the pair a dual black hole system. Observatories catch glimpses of two bright X-ray sources or see telltale double peaks in emission line spectra. Even at this distance, the timescale for further decay can be short, perhaps only a few million years, if enough gas remains. The gas does more than feed. Its drag acts as a second brake, robbing the pair of angular momentum faster than stars alone could manage. Eventually, the distance shrinks to a few light-years. Now the two black holes form a bound binary, orbiting their common center of mass every few years or even months. At this stage, the environment matters greatly. If the merged galaxy's core is still thick with gas, the binary can harden quickly, the gas acting like glue, forcing the orbit tighter. In a gas-poor core, progress can stall, the infamous final parsec problem. The binary might linger for hundreds of millions of years, kicking away passing stars and carving a low-density cavity around itself. Yet even in dry conditions, gravity has another trick: three-body encounters. When a star wanders too near the binary, it can be slingshot out at high speed, stealing orbital energy and helping the two black holes inch closer still. Once the separation falls below roughly 1/100th of a light-year, gravitational waves take over. At that point, the pair lose energy directly to ripples in space-time. The final spiral accelerates rapidly. In the last minutes, the black holes circle each other many times per second, radiating more power in gravitational waves than all the stars in the visible universe combined. Then they merge. A burst of distorted space sweeps out at light speed, carrying the news of a new, heavier black hole. If the outgoing gravitational waves are emitted unevenly, they can give the newborn black hole a recoil. Simulations suggest that kicks of hundreds or even thousands of kilometers per second are possible, depending on spin directions. In lightweight galaxies, such a kick might eject the black hole entirely, leaving a core without a central monster. In heftier hosts, the black hole may only slosh around for a while before sinking back to the middle. For the galaxy that keeps its remnant, a fresh cycle of feeding often follows. The merger has already funneled gas toward the core. Shock heating and stellar winds now settle, allowing some of that gas to cool again. The black hole, now more massive, lights up with renewed vigor. Jets and radiation pour out, regulating further growth in the surrounding bulge. Star formation, once frantic, slows. Over time, the galaxy settles into a new shape, maybe an elliptical blob or a fat-armed spiral, its history written in shells of stars and faint tidal streams. Cosmological simulations show that this dance repeats across cosmic time. Small galaxies merge to form bigger ones. Their black holes merge as well. Each step up the hierarchy brings a chance to double or triple black hole mass in a single event. Gas-rich mergers dominate the early universe, when cold material is plentiful and galaxies are compact. Later, as gas supplies dwindle, dry mergers, stars and dark matter but little fuel, take over, still adding mass through black hole coalescence, even if accretion slows. This hierarchical growth helps explain several observations. First is the tight link between a galaxy's bulge mass and its black hole mass. Every major merger both enlarges the bulge and adds to the central black hole, keeping them roughly in step. Second is the rapid appearance of billion solar mass black holes less than a billion years after the Big Bang. Multiple quick mergers among seed black holes, perhaps augmented by direct collapse or primordial seeds, can produce giants. Finally, the process predicts that many galaxies in the nearby universe should host stalled binaries or offset black holes, relics of mergers still underway. Detecting such systems is a major goal. Radio arrays hunt for pairs of close jets. Space telescopes look for periodic flares that might signal two black holes orbiting each other. LISA will allow astronomers to listen for low-frequency gravitational waves from binaries in the final 1,000 to million year in spiral, objects too widely spaced for ground-based detectors. Those signals will map merger rates across cosmic history, showing how often galaxies unite and how their central monsters grow. Clusters of galaxies where mergers happen more frequently host the most massive black holes known, objects like those in Phoenix A or Ton 618. Their sizes echo the history of repeated collisions among the cluster's member galaxies. Even at the level of the cosmic web, where filaments feed gas into growing nodes, mergers enhance the flow, driving both starbursts and black hole growth. Watching two galaxies collide in the night sky is rare, the timescales are vast, but telescopes freeze those moments at every stage in every direction. Some show the first tidal bridges forming. Others reveal tight, dusty cores where two bright points glow side by side. A few, caught in X-rays or radio, display cavities carved by jets, echoes of a merger long past. Put together, these snapshots tell a single sprawling tale: how gravity pulls galaxies into unions, how their black holes meet, and how those meetings forge the heaviest anchors in the cosmic sea. Swallowing the universe. Imagine a black hole growing larger and larger. As it gains mass, its event horizon expands. This happens because the size of a black hole's event horizon is directly related to its mass. The more mass, the bigger the radius. In theory, if a black hole kept swallowing material, stars, gas, dust, planets, it could grow without limit. So why not just keep going? Why not eat galaxies, clusters of galaxies, and eventually everything? One reason for why this might never be possible is that the universe is expanding. Space itself is stretching. That expansion isn't something black holes can easily overcome. In fact, it works against them. Distant galaxies aren't just moving away from us, they're moving away from each other because the space between them is growing. Even a black hole with enormous gravity can't chase down something that's being carried away by the fabric of space itself. In many ways, the universe is expanding too fast for any one object, even a supermassive black hole, to catch everything. This becomes especially clear when we talk about the observable universe. There's a limit to what we can see because light takes time to reach us. Galaxies that are now more than about 46 billion light-years away are beyond that horizon. Their light hasn't had time to get here since the Big Bang. And because the universe is expanding faster than light over long distances, much of it is moving away from us forever. A black hole would face the same problem. There's no way for it to pull in regions of space that are being carried away faster than its gravity can act. It's not just about pulling on objects. It's about outrunning the expansion of space. And gravity doesn't travel faster than light. That being said, there's a twist. What if the universe weren't expanding forever? What if one day the expansion slowed down and reversed? That was a serious idea in cosmology not too long ago. For much of the 20th century, scientists debated whether the universe would keep expanding or eventually collapse. If there were enough matter in the universe, enough gravity, the expansion could halt and then reverse. This scenario is called the Big Crunch. In it, everything would eventually fall back in on itself. Galaxies would get closer, temperatures would rise, and all matter might collapse into a single point, not unlike the state the universe started in. If that were to happen, then yes, a single black hole could potentially form, or at least a state very much like one. The difference is important. In this scenario, we're not really talking about one black hole growing until it eats everything else. We're talking about the entire universe turning into a black hole together. Every particle, every photon, every galaxy would be part of that collapse. The universe itself would be the black hole. In fact, there's an argument that our universe might already resemble a black hole in some ways. Think about it. There's a horizon beyond which we can't see. There's a fixed amount of energy and mass inside that horizon. There's even something like temperature, connected to the expansion of space and the cosmic background radiation. This has led some physicists to suggest that the universe could be understood using the same tools we use to describe black holes, just flipped inside out. In a black hole, the event horizon hides the singularity from outside view. In the universe, the cosmic horizon hides the rest of space from us. It's a poetic symmetry, even if the physics is still not fully worked out. There's also the idea of a multiverse a vast landscape of possible universes beyond our own. In some theories, especially those based on inflation, each pocket of the multiverse can expand into its own universe with its own laws. Some physicists have speculated that black holes in our universe might even give rise to new baby universes inside. In that case, the question of one black hole swallowing this universe becomes a doorway to other worlds. Rather than swallowing all of space, a black hole might actually birth more of it. Still, we return to the real limits. Black holes grow by eating matter, and there's only so much matter nearby. Most galaxies have their own central black hole. Most of these black holes are content to sit where they are, growing slowly if at all. Even the mergers of galaxies don't result in runaway consumption. They are local events on cosmic scales. A black hole in one galaxy doesn't pull in stars from a galaxy across the sky. Distance wins. Another barrier is time. Even if a black hole had unlimited food and no cosmic expansion to fight, it would still take time to grow. It takes millions of years just to double in size if it's eating efficiently. Growing to the size of the observable universe would require time far beyond what the universe has been given, especially since feeding slows as the black hole gets bigger. And yet, the idea makes us rethink what a black hole really is. Is it a region with an event horizon? Is it something that traps light? Or is it more than that? A structure connected to the deepest laws of space, time, and information? Some theorists go so far as to suggest that the entire universe could be described as a kind of hologram, where all the physics inside emerges from rules defined on a cosmic horizon. That's not the same as a black hole swallowing the universe, but it blurs the boundary between the two ideas. So the answer, in practical terms, is no. A single black hole can't swallow the universe. But the real answer, the deeper one, is more interesting. The universe and black holes might be different expressions of the same thing. Both bend time, both have horizons, both obey strange rules about entropy, temperature, and information loss. In trying to answer this question, we learn about the edges of what reality itself might be. Is the universe tipping toward a black hole fate? Imagine the universe not just as stars and galaxies scattered through space, but as one enormous physical system. Everything in it, from the tiniest particles to the largest clusters, follows rules laid out by thermodynamics. Over time, hot stars burn out, leaving behind cold remnants. Gas clouds are pulled into black holes or spread so thin they barely interact. Collisions become rarer. Motion slows. In the far future, if nothing new intervenes, the universe heads toward what's called heat death, a state of maximum entropy where everything is evenly spread and no more work can be done. Among all the objects in the universe, black holes are the most efficient at storing entropy. This may sound strange. They seem like simple, featureless objects, just regions of space from which nothing escapes. But their simplicity is exactly why they have so much entropy. A single black hole can hold more entropy than any other object of the same mass. It's packed with possibilities, even though we can't see inside it. This idea was made famous through the work of physicists like Jacob Bekenstein and Stephen Hawking. They showed that black holes obey thermodynamic rules. They have temperature, they have entropy, and the entropy of a black hole is proportional to the area of its event horizon, not the volume inside. That was surprising. It meant that as a black hole grows, its entropy rises rapidly. The bigger it gets, the more it dominates the overall entropy of the universe. So now imagine the distant future. Stars are gone, planets are cold, galaxies have scattered. What remains are black holes, sitting quietly in the darkness, slowly evaporating over unimaginable timescales through Hawking radiation. As they radiate, they shrink. That radiation is random and low energy, spreading entropy into space. Eventually, even black holes vanish, leaving behind a cold, flat universe filled with low-temperature radiation and scattered particles. Nothing happens after that, because nothing can happen. This is the ultimate high-entropy state. But there's another way to look at this evolution. Instead of black holes disappearing, What if the entropy of the universe is pushing things toward becoming one giant black hole? It's a strange idea, but it follows from how thermodynamics works. If a single black hole can store more entropy than everything else, then forming one could be seen as a kind of final move, a way of reaching the highest entropy state possible. A universe-sized black hole would be the end point of structure, energy, and even space itself. No further change would be possible. There's a tension here between two visions. In one, the universe expands forever, and entropy spreads outward until everything is cold and diffuse. In the other, gravity wins in the end, and everything falls together into one all-encompassing collapse. Both scenarios lead to high entropy. Both lead to an end. But only one feels like the universe becoming a black hole. To explore this further, scientists have studied how black holes shape the entropy budget of the universe. They've calculated how much entropy stars and galaxies have compared to black holes. The results are clear. Black holes already dominate. A single supermassive black hole at the center of a galaxy can have more entropy than all the stars in that galaxy combined. And if you add up the entropy from all known black holes, it far outweighs the rest of the visible universe. This leads to a strange conclusion. If entropy is always increasing, and black holes are where most of that entropy is concentrated, then perhaps black holes aren't just byproducts of the universe. They are its destiny. Not in a poetic sense, but in a physical one. The rules of thermodynamics might be pointing everything in one direction, toward black holes. Still, we have to be careful. Just because something holds a lot of entropy doesn't mean everything is headed that way. The universe isn't just a closed system of gas cooling in a box. It's expanding, and that changes the rules. As space stretches, it creates new room for entropy to grow. The universe can keep spreading out, forming new structures or dissolving them. In this context, the formation of a single giant black hole seems less likely, unless something changes dramatically. Some physicists have explored ideas where the entire universe might already be a kind of black hole. If you take all the mass in the universe and ask how large a black hole it would form, you get something close to the size of the observable universe itself. That's not proof, it's more of a coincidence. But it's one that stirs curiosity. These ideas push into the realm of quantum gravity and holographic principles, where space-time may be emergent rather than fundamental. In some models, everything we experience is encoded on a boundary, like a projection on a screen. In those models, entropy, black holes, and the shape of the universe are all linked. Even if no single black hole ever swallows everything, the rules they follow help describe where things are headed. In the end, whether through expansion, collapse, or slow evaporation, they show us that the universe is always moving towards something simpler, colder, and quieter. A future where entropy reigns and the echoes of structure fade into silence. Is gravity dragging the universe into one giant collapse? Galaxies aren't just scattered randomly. They form a kind of structure, like threads in a spider's web stretched across the cosmos. This cosmic web is made up of filaments of galaxies, clusters at intersections, and giant voids in between. It's the shape of matter on the largest scales we can see, and it's all tied together by gravity. Gravity, more than any other force, is the architect of the universe's shape. Over billions of years, it has slowly pulled gas, dust, and dark matter into clumps, from which stars and galaxies have formed. Gravity doesn't work fast, but given enough time, it turns a smooth universe into one filled with structure, layered and laced together across unimaginable distances. At the hearts of galaxy clusters are deep gravitational wells, places where the pull of gravity is stronger than anywhere nearby. These wells are made of galaxies, hot gas, and even larger amounts of dark matter. The deepest wells can span millions of light years across and weigh more than 1,000,000,000,000 times the mass of the Sun. These wells act like basins. Just as water flows downhill into a valley, matter in the universe flows toward these gravitational low points. Now the question begins to shift. What happens when these giant wells start to merge? Imagine two clusters of galaxies, each with its own central well of gravity. They begin drifting toward each other, drawn by their mutual pull. Over hundreds of millions of years they collide, not in a sudden crash, but in a slow, drawn-out process. Galaxies within them pass by one another, mostly without touching. But their dark matter halos mix, and the gas between galaxies gets heated and compressed. A new, even deeper gravitational well forms from the merger. We've seen examples of this happening. One famous case is the Bullet Cluster, where two galaxy clusters are in the middle of a slow-motion smash. Their dark matter has passed through largely unaffected, while the hot gas lags behind, showing clear signs of the ongoing collision. Observations like this confirm that gravity continues pulling larger and larger structures together, even as the universe expands. Could all the clusters, superclusters, and filaments eventually fall together into a single, ultimate collapse? The expansion of the universe is strong enough that most galaxies beyond our local group are moving away from us and will never come back. Gravity still works, but only on local scales. It can pull galaxies into clusters and clusters into superclusters. But beyond a certain point, expansion wins. The cosmic web may stretch, but it won't collapse into a single knot. Even so, the question remains whether large regions, larger than clusters but smaller than the whole universe, could still fall together. Simulations of cosmic evolution suggest that some of the largest structures, like the Shapley supercluster or the Great Attractor region, are still pulling in matter from hundreds of millions of light-years away. Their gravity is strong enough to overcome expansion locally, and they continue growing. These structures are enormous, but they still only contain a small part of the total universe. They aren't connected in a way that would allow a true universal collapse. Instead, the universe seems to be dividing. Some regions are bound together by gravity and will merge over time. Others are being pulled apart by expansion, moving out of reach forever. So the idea of one giant collapse, everything falling into one spot, is unlikely. Gravity may be strong on local scales, but dark energy dominates on the largest ones. The universe isn't pulling together into a single whole. It's stretching apart into isolated islands of structure. Still, gravity leaves behind clues that make the picture more complicated. One of these is gravitational lensing. These distortions show us the invisible scaffolding of dark matter holding galaxies in place. Lensing maps reveal just how deep these gravitational wells are, and how connected they remain. In some cases, light paths curve in ways that suggest long filaments still tug on one another across vast distances. And then there's cosmic flows, the movement of galaxies not just from expansion, but from gravitational influence. Some galaxies drift toward massive structures, even if they're millions of light-years away. These flows map out how matter is responding to gravity, forming rivers of motion that lead toward deeper and deeper wells. These flows show that gravity is still shaping the large-scale map of the universe even now, but they also show limits. They don't all lead to one place. Instead, they lead to many deep points in the web, places where matter will eventually gather and settle. It's not one collapse, but many local ones. Some scientists have wondered if these large gravitational basins could form something like regional black holes. Not true black holes, but regions so dense and connected that they behave similarly on huge scales. These ideas hint that gravity, even now, is working toward a kind of local closure. It can't pull in the entire universe, but it can still shape it into deeper and deeper pockets of structure. The end result is a universe that breaks into zones. Each zone, if isolated, might form its own deep well, perhaps even ending in a supermassive black hole that absorbs all nearby mass. But these zones are cut off from one another by the expansion of space. Each becomes its own quiet, dark island. In this way, gravity still plays the role of a sculptor. It pulls, deepens wells, connects galaxies, and keeps reshaping what's nearby. In each of the local collapses, in every deep well that forms, we see the fingerprint of gravity's long reach. We see that even though the universe won't fall into one black hole, it still may, piece by piece, drift toward quieter, colder, more isolated ends, each shaped by the invisible pull of gravity's unrelenting hand. White holes, fiction, fluke, or the other side of reality. There exists a mathematical mirror image of a black hole. It's called a white hole. Unlike a black hole, which pulls everything in and lets nothing out, a white hole does the opposite. Nothing can enter it. Instead, it only throws things out. It's as if time itself runs backward. The idea of white holes came out of the same equations that gave us black holes. In the early 20th century, when Albert Einstein developed his theory of general relativity, scientists found that his equations allowed for multiple strange possibilities. One of those was the black hole. Another, less known and less understood, was the white hole. Mathematically, if you flip the direction of time in the equation for a black hole, you get a white hole. That's why people say it's a time-reversed version. For every bit of matter that falls into a black hole and vanishes from view, a white hole would be the opposite, a place where matter suddenly appears and spreads outward. No cause, just an effect. In the full idealized version of the math, a white hole is part of the same structure as a black hole. They connect through a bridge, a tunnel that links two regions of space-time. This is what's called a maximally extended Schwarzschild solution. And that bridge? Many scientists think it's a kind of wormhole. The idea is that something could fall into a black hole in one region of the universe and come out of a white hole somewhere else. The problem is, that's not what we see in reality. In the actual universe, black holes form from collapsing stars. But white holes don't have any known way to form. There's no process in the observable universe that naturally leads to a white hole appearing. No cloud of gas collapses into one. No supernova explodes into one. They simply don't arise in our world, at least not in any way we've seen. That's one reason they're still theoretical. Another reason is stability. If you try to simulate a white hole in a realistic model, it doesn't behave well. It's unstable. Even the tiniest disturbance in space, like a single particle approaching it, causes the white hole solution to collapse or turn into a black hole instead. That makes it very unlikely we'd see one in nature, even if they did somehow form. Still, the idea hasn't completely gone away. Some physicists continue to explore whether white holes could exist under special conditions, not as full-size cosmic objects, but maybe as something smaller. One possibility is that white holes are related to quantum gravity. That is, they might only make sense when we combine general relativity with quantum physics, something scientists are still working on. A group of researchers working on loop quantum gravity, a theory that tries to explain space and time at the smallest scales, has proposed that white holes might be the result of what happens at the center of a black hole. According to this idea, when matter collapses into a black hole, it doesn't hit a point of infinite density. Instead, quantum effects cause a bounce. After a very long time, the black hole could transform into a white hole and release its contents back into the universe. This would take billions or even trillions of years, far longer than the current age of the universe. But it offers a kind of recycling path. Rather than matter being trapped forever, it would eventually come back out. This concept, sometimes called a Planck star, is one of the few ways white holes might make physical sense. There's another place where white holes have been considered, at the birth of the universe itself. Some cosmologists have wondered whether the Big Bang could have been the result of a white hole. That is, maybe our entire universe was ejected from a white hole in another region of space. It's a bold idea, but there's no direct evidence to support it. Even though we haven't observed a white hole, astronomers keep their eyes open. One idea is that white holes might briefly appear as flashes of high-energy radiation, short bursts that don't follow the usual patterns. Gamma-ray bursts, for example, are some of the most powerful explosions in the universe. Could a few of these be white hole events? So far, none of the data fits that description. But the search continues. There was also some speculation years ago about strange repeating fast radio bursts, FRBs, as potential signs of exotic phenomena like white holes. These are brief, bright pulses of radio waves that come from distant galaxies. Most of them are likely caused by magnetars or neutron star interactions. But a few show unusual behavior that scientists still don't fully understand. For a short time, white holes were proposed as a possible explanation. That idea hasn't gained wide support, but it reflects how white holes stay on the edge of the conversation. One of the biggest obstacles to white holes is the issue of entropy. When things fall into a black hole, the system becomes more disordered. The information gets locked behind the event horizon. But a white hole, by definition, pushes things out in an ordered, low-entropy state. That violates the second law of thermodynamics unless there's some way to account for it. So for a white hole to work, it must include a deeper understanding of information and entropy. That's one reason why white holes often appear in discussions about the information paradox, a major problem in black hole physics. And then there's the issue of observation. A black hole reveals its presence through its surroundings. Gas swirling around it, light bending near it, stars orbiting it. But a white hole would show the opposite behavior. There would be a sudden outflow of matter and energy, with no clear cause. If we saw a star-like object suddenly appear and blast material outward before fading away, that might be evidence. But nothing like that has ever been seen. So are white holes real? Are they just a mathematical fluke, or could they be hints of a deeper structure in space-time? Right now, no one knows for sure. They remain one of the most exotic possibilities allowed by Einstein's equations. 1 foot in science, 1 foot in imagination. They don't appear in the sky, but they show up in the chalk dust of physics seminars and the simulations of computer models. White holes force us to think not just about gravity, but about time. Not just about collapse, but about emergence. Whether or not they exist in our universe, they continue to challenge the way we think about black holes, space-time, and what lies beyond the veil of the event horizon. The black hole information paradox. Quantum physics has a rule. Information can't be destroyed. In quantum theory, information is tied to the exact state of particles. If you knew everything about a system, the energy, spin, position, and momentum of every particle, you could, at least in theory, rewind time and find out how that system started. That's not just a nice idea. It's built into the math. Quantum mechanics doesn't allow for total erasure. So when Stephen Hawking showed that black holes can evaporate over time through Hawking radiation, it raised a serious problem. The radiation doesn't carry any clear signs of what the black hole was made from. It's thermal. It has no structure or pattern that reveals the past. When a black hole evaporates completely, all that's left is a thin cloud of random-looking radiation. No map back to the original object, just heat. Where did the information go? Some physicists said, it's gone. Black holes truly erase information. That would make them exceptions to quantum rules. This view was shocking, because it meant that physics might not be as secure as we thought. If information can vanish, then quantum mechanics, one of the most tested theories in all of science, might be incomplete. Others argued the information isn't lost, it just looks like it is. They believed that there had to be a way, hidden in the math or physics, for the information to survive. Maybe it was stored inside the black hole somehow, or maybe it escaped with the radiation in a way we hadn't figured out yet. This argument went on for decades. Hawking himself first claimed that information was destroyed. Later, he changed his mind and said it might be preserved, possibly encoded in the radiation after all. But the details were missing. What kind of mechanism could allow such a thing? The radiation appeared thermal, random. How could randomness contain order? One idea was that the radiation wasn't truly random. Maybe it carried small imprints, entangled bits of quantum data, connected to the things that fell into the black hole. Entanglement is a strange part of quantum theory where two particles can share a state, even across great distances. If you measure one, you instantly learn something about the other. Some researchers thought that the radiation coming out of a black hole might be entangled with the interior, in just the right way to preserve information. Over time, the full pattern of radiation might reflect everything the black hole had swallowed. But that idea led to a new problem, called the firewall paradox. If the outgoing radiation is entangled with the inside, and also with earlier radiation, then quantum rules about entanglement start to break down. Something has to give. To fix this, one suggestion was that the event horizon of a black hole isn't smooth like Einstein imagined. Instead, it might be a wall of high-energy particles, a firewall, that would burn anything trying to cross it. This would violate the long-held belief that a person falling into a large black hole would pass the horizon without feeling anything special. The firewall idea challenged general relativity head-on. Other proposals tried to avoid firewalls. Some said the information might be stored on the surface of the black hole. This is the idea behind black hole complementarity, which suggests that the information never really falls in, at least not from an outside perspective. Instead, it gets smeared across the surface. To an outside observer, everything that falls into the black hole gets recorded on its surface and slowly leaks back out as radiation. To someone falling in, the experience feels normal, but those two perspectives can't be compared directly. You can't both fall into a black hole and watch from the outside, so maybe there's no contradiction. Each view tells a consistent story within its own frame. This brings in the idea of holography, an idea that took on new strength in the 1990s and 2000s. The holographic principle suggests that a three-dimensional space can be described entirely by information on a two-dimensional boundary. In black hole physics, this means that everything inside the black hole might be encoded on its event horizon. That way, information is just relocated. Another approach came from studying the anti-de Sitter conformal field theory, or ADS-CFT. This theory connects a kind of space with gravity, the anti-de Sitter space, to a system without gravity, the conformal field theory. In these models, everything happening in the gravitational space can be fully described by the non-gravitational side. That's a major clue that information might never be lost, because the field theory is quantum, and quantum theories don't allow information loss. More recently, detailed calculations involving the geometry of space and entanglement entropy suggested that black holes start to release information halfway through their evaporation. This Page curve, named after physicist Don Page, describes how the entropy of the radiation rises at first, then falls, just like it would if information were preserved. Early on, radiation seems random, but as the black hole shrinks, the later radiation becomes correlated with the earlier parts. In this view, the full history of the black hole is not lost. It just takes time to emerge. These calculations rely on deep mathematics and tools from quantum gravity. One technique involves replica wormholes, strange shortcuts in space-time that seem to appear when trying to average over different quantum histories. These methods are still being debated, and they don't give a full picture of what's happening inside the black hole. But they support the idea that information might escape. Still, there's no final answer. Some physicists think the entire paradox shows that we need a better theory of quantum gravity, and until we have that, black holes will remain mysterious. What began as a simple question, what happens when something falls into a black hole, has led to decades of research, arguments, and discoveries. It has connected distant parts of physics, from particle theory to cosmology. It has raised questions and pushed scientists to look deeper. The black hole firewall hypothesis, a barrier to infinite growth. The idea was proposed by physicists Almheri, Marolf, Polchinski, and Sully in 2012, and it suggested that to preserve quantum mechanics, the event horizon couldn't be as gentle as previously thought. Instead, there would be a high-energy region at the horizon strong enough to incinerate anything that crosses it. If the information is preserved, then it has to be encoded somewhere, and the firewall could be the mechanism that prevents it from disappearing entirely. However, the concept comes with a range of difficulties. One of the main problems is that it contradicts the so-called no-drama principle in general relativity. According to this principle, anyone falling into a sufficiently large black hole should not feel any abrupt or violent effects when crossing the event horizon. If firewalls exist at black hole horizons, it would mean that the fundamental understanding of black holes needs to be rewritten. One of the most difficult aspects of the firewall hypothesis is that it's hard to test. We cannot currently observe the inside of a black hole, let alone probe the behavior of any potential firewall. This makes the idea speculative, at best. However, it has nevertheless pushed the scientific community to re-examine some of the most fundamental aspects of black hole physics. There's also the issue of what happens to the black hole itself if firewalls exist. Black holes are already strange, mysterious objects, but the presence of a firewall would suggest that there's a limit to how large a black hole can grow. If everything that falls into a black hole encounters this wall of energy, then there may be an upper bound to the size of the black hole. This could introduce a new kind of self-regulation for black holes, preventing them from continuing to grow endlessly. Another important question raised by the firewall hypothesis is whether it would have any impact on the growth of supermassive black holes. If firewalls exist, they could place a fundamental limit on the size of these giants. It's unclear whether this would prevent the black holes from continuing to grow, or whether they would just grow more slowly. But the very idea that there's a hard limit on growth is a radical departure from the current understanding. The firewall theory is far from being universally accepted. Some scientists believe that it's an unnecessary complication and that the information paradox can be resolved without resorting to the idea of a firewall. In many ways, the firewall hypothesis exemplifies the challenges faced by physicists trying to understand black holes. These objects lie at the intersection of general relativity and quantum mechanics. And when these two theories meet, the results can be baffling. For now, the firewall remains a theory, one that might one day change the way we look at black holes forever. Holographic universe. Are we just the surface of a giant black hole? The holographic principle originated in the 1990s, primarily through the work of physicists Gerard T. Hooft and Leonard Susskind. They came up with the idea that the information that falls into a black hole is stored on its surface, much like how a hologram stores three-dimensional information on a flat surface. In this view, the entire interior of the black hole would be a kind of projection, a 3D illusion based on the data stored on its two-dimensional boundary. The holographic principle suggests that the entire universe, not just black holes, could follow the same rule. In this view, the 3D world we experience might be a projection of data stored on the boundary of the universe, similar to how a hologram creates a three-dimensional image from a two-dimensional surface. This boundary could be the event horizon of a gigantic black hole that contains our universe. If true, it would mean that everything we see and experience, our reality itself, is just a projection of information. All the atoms that make up our bodies, all the stars in the sky, and even the fabric of space and time could be encoded on the surface of a vast cosmic horizon. Our universe, in this sense, would be an elaborate illusion, a kind of cosmic simulation playing out on the surface of a black hole. The ADS-CFT correspondence implies that everything that happens inside a black hole can be understood by studying the boundary of the black hole, where space-time remains intact. It's as though the universe is a giant projection, where the real fundamental laws of reality reside on the surface, and everything else is a consequence of those laws. In the holographic model, space and time as we understand them may not be fundamental at all. Instead, they might be emergent properties that arise from the underlying data encoded on the boundary of the black hole. In this view, what we perceive as the continuous flow of time and the vast expanse of space could be the result of a kind of cosmic encoding, with the true underlying structure of reality being something far different from what we experience. The holographic principle is a mathematically consistent framework that fits well with both quantum mechanics and general relativity, and it offers a potential solution to some of the most vexing problems in modern physics. In fact, it has already had significant success in certain areas of physics. For instance, it has been used to study the behavior of black holes, the nature of quantum gravity, and the structure of the early universe. In some ways, the holographic universe theory offers a more natural and elegant solution to these problems than other, more traditional approaches. By viewing the universe as a projection from a higher dimensional surface, the theory can reconcile some of the apparent contradictions between quantum mechanics and general relativity. But are we really mere projections? And if so, what does that mean for our understanding of the universe's structure and the fundamental nature of reality itself? The black hole multiverse. Infinity tends to be a sign that our current models are missing something important. Many physicists believe that we'll eventually need a theory that combines general relativity with quantum mechanics to fully understand what's going on inside black holes. Such a theory of quantum gravity might reveal that the singularity isn't an endpoint after all. Instead, it could be a transition point. One suggestion is that when matter falls into a black hole and compresses past a certain limit, quantum effects push back. Instead of collapsing forever, the effects push back. Instead of collapsing forever, the core of the black hole might reach a minimum size, something tiny but non-zero, and then rebound. That bounce could release energy or space-time into another region, one we can't see from our side. That region could expand on its own, forming a new universe. It would be sealed off from us, hidden behind the event horizon. This idea has roots in work from the 1980s and 1990s, but it continues to attract attention today. Physicist Lee Smolin, for example, proposed a version of this theory known as cosmological natural selection. In his model, every black hole gives birth to a new universe with slightly different physical constants. Gravity might be stronger, the speed of light slightly faster, or particle masses slightly heavier. Most of these baby universes wouldn't be stable, but a few might develop conditions that allow stars, galaxies, and eventually black holes to form again. Those in turn would create more baby universes. It's a cycle that echoes evolution. Universes that are good at making black holes produce more offspring. Over time, the multiverse could become filled with universes fine-tuned for black hole formation, and ours, where black holes are common, might be one of them. It's a way to explain why the physical constants in our universe seem so well suited for complexity and structure without needing a supernatural explanation. We're here because we live in a universe that's good at reproducing itself through black holes. Another version of this idea comes from loop quantum gravity, which describes space-time as a network of loops at the smallest scale. In this model, when matter reaches extremely high densities inside a black hole, the loop structure resists further collapse. It turns what would be a singularity into a bounce, releasing matter and energy into a new region of space-time. That region, cut off from our own, could undergo a kind of mini-Big Bang. String theory, too, has versions of the baby universe idea. In some models, black holes connect to other dimensions or branes, hidden surfaces that may lie parallel to our own universe. When matter falls into a black hole, it might travel through these dimensions and emerge elsewhere. To us, the black hole seems like an ending, but from the inside, it might be the start of a whole new reality. If a new universe is born inside a black hole, it would be completely disconnected from ours. We couldn't observe it directly, but that doesn't mean we're without clues. Some researchers have looked for patterns in the cosmic microwave background for signs that our universe came from such a process. If our universe began as a black hole in another universe, there might be subtle marks in the early light, like imprints of the parent universe's structure. There's also the question of information. According to the rules of quantum mechanics, information can't be destroyed. But black holes, if they just vanish into nothing, seem to do exactly that. This is known as the black hole information paradox. If, however, the matter and information that fall into a black hole end up in a new universe, the information might not be lost, It's just gone somewhere else. That could be one way out of the paradox. Still, many physicists remain cautious. There's no solid proof for baby universe theory, and the mathematics involved is difficult. Some versions of the theory suggest the new universe would pinch off entirely, like a soap bubble breaking away from another. Others suggest a wormhole-like connection might remain, but would collapse so quickly it couldn't be traversed. Another issue is energy. If a black hole forms in our universe, and a new universe is born inside it, where does the energy for that universe come from? Some theories suggest that the energy is borrowed from the vacuum, the baseline state of space itself. In that case, the creation of a baby universe wouldn't violate the conservation of energy, at least not in a way that breaks physics. In some models, the entire observable universe from the outside would just look like a black hole in a higher dimensional space. From the inside, we'd see a world expanding from a big bang. In this scenario, the outer region would be forever hidden from us. But the math describing a black hole's interior and the structure of our universe would match. We don't have the tools yet to know for sure. The mathematics is hard, the observations limited, but the questions are worth asking. Cosmological horizons versus event horizons. Which one wins? The black hole's event horizon stops us from seeing what goes on inside. Even with the best theory, we can only guess what lies beyond that boundary. Is it a singularity, a quantum fuzz, a tunnel to another universe? We don't know. The cosmological horizon is more subtle. It doesn't trap matter the same way, but it traps information. Any event that happens beyond this horizon is lost to us. It's a kind of separation by acceleration. A distant galaxy might send out light in our direction, but by the time the light travels a bit, the space in between has stretched even more. Over time, these galaxies fall off the edge of visibility. They haven't gone anywhere, but they've crossed a limit where we can never see them again. In that way, both horizons impose the same kind of limit. They divide the universe into a region we can observe and one we can't. They are boundaries not made of matter, but of causality. Who can affect whom, and who is beyond reach. But there's an important difference in how these boundaries behave. A black hole's event horizon is fixed once the black hole forms. It might grow if more matter falls in, but it's always there, always marking the line where escape is impossible. On the other hand, the cosmological horizon changes over time. In the early universe, when expansion was slower, the horizon was smaller. As expansion speeds up, especially with the influence of dark energy, the horizon moves further out. But paradoxically, even as the observable universe expands, some galaxies are disappearing over the edge. It's a horizon that shifts, not a static wall, but a moving one. This has strange consequences. There are objects we can see today, distant galaxies, brilliant quasars that won't be visible in the far future. Not because they've faded or died, but because the universe's expansion will pull them beyond our reach. Their light will redshift, stretch, and eventually vanish. The future observer will live in a lonelier universe, surrounded only by nearby galaxies, with the distant ones erased not by time, but by the expansion of space. This makes the cosmological horizon more dynamic, more elusive. It's not as harsh as the black hole's horizon, but it's just as real in terms of cutting off information. Over time, more and more of the universe will fall beyond the line, unreachable and unknowable. Some researchers ask whether the event horizon and the cosmological horizon might share more than just metaphor. Both have thermodynamic properties. Black hole horizons have entropy proportional to their surface area. The same is true of cosmological horizons. The famous de Sitter space, a model of a universe with only dark energy, has a cosmological horizon with entropy and temperature. In both cases, the boundary can radiate, hold information, and perhaps even obey similar rules. Maybe these horizons aren't just mathematical tools, but fundamental pieces of how the universe works. Maybe boundaries like this are the key to understanding space-time, information, and even the nature of gravity itself. If so, the question of which horizon wins becomes deeper than just which one hides more. Are we more trapped by the black hole's event horizon, hiding its interior? Or are we more limited by the cosmological horizon, hiding the farthest reaches of space? From the point of view of a spacecraft near a black hole, the event horizon is the final boundary. Cross it and you vanish. But from the point of view of a cosmologist studying the universe, the edge is out there, past the most distant galaxies, always moving. What lies beyond will never be known, not because we're not clever enough, but because the rules of light and time forbid it. In a holographic universe, where the contents of space are encoded on boundaries, both the black hole and the cosmos might be expressions of the same underlying structure. The two types of boundaries might not compete, but mirror each other. Whatever theory comes out on top, the fact remains. We are surrounded by horizons, some local, some cosmic. They shape what we can see, what we can measure, what we can predict. Planck stars and the bounce theory. Is there a way out of the singularity? What happens when gravity is extremely strong and space is extremely small? One proposal is the idea of a Planck star. It's named after the Planck scale, the smallest scale where quantum effects of gravity are expected to become strong. At that scale, space and time may not be smooth and continuous, but fuzzy and grainy, shaped by quantum fluctuations. A Planck star is what might form if a collapsing star is stopped, not by degeneracy pressure or by radiation pressure, but by the quantum nature of space itself. In this view, the collapsing matter never actually reaches the singularity. Instead, when the density becomes high enough, approaching the Planck density, quantum effects push back. Gravity becomes repulsive at very small scales. The collapse halts. The core stabilizes into a tiny but finite object of incredible density. This core resists further compression and acts like a bounce point. This Planck star is hidden from view, buried beneath the event horizon. From the outside, it behaves just like a regular black hole. But inside, something very different is going on. Over vast amounts of time, the Planck star could re-expand. The matter inside, once collapsed, may eventually bounce back and be released. In this view, a black hole is not a one-way trap, but a slow-motion event. From our perspective, it would look like a black hole slowly evaporating. But from the inside, the story could be very different. If black holes are really Planck stars, and they eventually release their contents, then the information within them might not be lost after all. It would just be trapped for an incredibly long time. Of course, there's no direct evidence for Planck stars yet, but some researchers believe that future observations could offer indirect clues. One idea is that the final stage of black hole evaporation, when the Planck star re-expands, might produce a burst of radiation. If so, these bursts could be seen as high-energy events in the sky. They might look like gamma-ray bursts or fast radio bursts, short but intense flashes of energy from deep space. These signals might carry the fingerprint of a bounce, a release of matter from a formerly collapsed core. Another idea is that microscopic black holes, if they exist, could evaporate more quickly and might show this bounce process in a timescale we can detect. Some searches for such events are already being done, though nothing conclusive has been found. If black holes don't end in singularities, but in bounces, then perhaps the same thing happened with the universe itself. The Big Bang might not have been the beginning, but the rebound from an earlier collapse. In this picture, the universe is like a giant Planck star, born from the bounce of a previous cosmos that had collapsed inward. This idea is sometimes called the Big Bounce, and it shares a deep connection with the Planck star concept. Both suggest that nature avoids infinities, and that the past is not cut off by singularities. Loop quantum gravity remains incomplete, and other models of quantum gravity, like string theory, offer different ideas. Some suggest that the singularity is resolved in other ways, through fuzzballs or holographic descriptions. There's no agreement yet on the right quantum gravity theory, and without direct experimental evidence, all such models remain uncertain. Still, the Planck star idea offers a compelling vision. It replaces a mathematical infinity with a physical object. It gives a possible route through the heart of a black hole. It also fits a growing trend in theoretical physics, seeking to patch the rift between relativity and quantum mechanics by finding new states of matter, new behaviors of space, and new rules that emerge only at the highest energies. Could a black hole replace the need for a dark energy explanation? Dark energy is considered one of the most important and elusive components of the cosmos, accounting for roughly 70% of the universe's total energy density. Yet, despite all its implications, we have no direct understanding of what dark energy actually is. It remains a theoretical construct introduced to explain the universe's acceleration, but with no known physical source or mechanism. However, there's a growing line of thought that suggests we might not need to invoke dark energy at all. Instead, the phenomena attributed to dark energy could be explained by the collective effects of black holes scattered throughout the universe. This hypothesis seeks to reshape how we view cosmic acceleration, proposing that the energy driving the expansion could actually stem from the immense presence of black holes rather than an unknown force spread throughout space. The effects of these black holes are far-reaching, affecting not only the galaxies they inhabit. This influence stems from their immense gravitational pull and, in many cases, the intense radiation and energetic jets that are expelled from the regions around them. But what if, beyond their localized gravitational effects, black holes could have a larger, more global impact? Dark energy is thought to have a constant density, meaning it doesn't dilute as space expands, leading to an ever-increasing rate of expansion. This explanation fits with current observations of the universe's accelerating expansion, but it comes with many unresolved questions, primarily about its true nature. It's possible that the accumulation of the space-time distortions of black holes across the universe could create an overall effect that is similar to the repulsive force attributed to dark energy. Some suggest that, over time, as galaxies continue to merge, the number of supermassive black holes would grow. These black holes would then exert more and more influence on the surrounding space, gradually driving the acceleration of the universe's expansion. This phenomenon could be especially relevant in the distant future, when the universe is dominated by black holes and their gravitational effects. One potential mechanism for how black holes might cause this effect is through a phenomenon known as space-time foam. Space-time, as described by general relativity, is a dynamic and malleable structure that responds to the mass and energy of the objects within it. Black holes cause dramatic curvatures in space-time. The idea of space-time foam suggests that the collective influence of these curvatures, produced by black holes, could distort the overall fabric of space in such a way that it leads to cosmic acceleration. In quantum mechanics, space-time itself is thought to be governed by probabilistic fluctuations at the smallest scales. This quantum foam is constantly fluctuating, and at certain scales, black holes might emerge as local effects of this deeper quantum structure. If black holes are connected to the underlying quantum state of the universe, their behavior, such as the accumulation of matter, the emission of Hawking radiation, or even the formation of event horizons, could have long-range effects on the expansion of the universe. Over time, these effects could accumulate and increase the rate at which the universe expands. This would allow black holes to take on a much more fundamental role in cosmology, not just as isolated phenomena within galaxies, but as active players in the large-scale evolution of the universe. One challenge with this theory is that we would need to find a way to connect these black hole effects with the observed phenomena of dark energy. While the gravitational effects of black holes are well documented, understanding how they could produce the constant, uniform acceleration that dark energy appears to cause is no simple task. It requires new insights into the nature of space-time and how it is affected by the collective presence of black holes. The existing models of dark energy describe it as a uniform, pervasive energy that doesn't interact much with matter. However, black holes exert a highly localized influence on their surroundings. If black holes are to account for dark energy, we would need to develop a framework that can explain how this local influence could scale up to cosmic proportions. One possibility is that black holes influence the larger structure of space-time through their accretion disks and their interactions with nearby matter. These interactions could send ripples throughout space, altering the expansion rate in ways that mimic the effects of dark energy. One key feature of dark energy is that its density remains constant. The black hole idea would have to account for this constant density. It's possible that black holes, as they accumulate mass and energy, could contribute to a background field effect, much like dark energy, which leads to a steady and constant push outward. Additionally, the idea that black holes could replace the need for dark energy doesn't entirely eliminate the role of other forms of energy. In fact, it could lead to a revised model where the combined effects of black holes, dark matter, and the energy content of the universe work together to shape the universe's evolution. Instead of being a singular force, dark energy might be a manifestation of a more complex interplay of cosmic phenomena. If this hypothesis is correct, it would represent a paradigm shift in our understanding of both black holes and the fundamental forces that govern the cosmos. While this theory still has much to prove, it opens up a new avenue of thought in our quest to understand the universe's accelerating expansion. If it holds, it could provide a more unified and elegant explanation for the forces shaping our universe. The last light, when black holes dominate the final era of the universe. In the very distant future, when the stars have stopped shining and galaxies have emptied of their glowing gas, the universe will enter the black hole era. Many would have been formed during the era of stars. Others may emerge from the collapse of neutron stars or from the merger of compact objects. There will be stellar mass black holes, the remnants of individual stars. There will be supermassive black holes at the centers of dead galaxies. And possibly, there will be intermediate black holes, strung along the leftover bones of cosmic structure. The black hole era won't be lively. The galaxies that once sparkled will become dim skeletons. Without stars, they'll be invisible, held together only by gravity. Black holes will drift through them like ghosts. Over time, many of these galaxies will lose their structure altogether. Gravity may fling the remaining stars and black holes into intergalactic space. Even planets, asteroids, and cold rocks will be ejected. The universe will continue to expand, stretching space and pushing these frozen fragments farther and farther apart. In this future, collisions still happen, but rarely. Two black holes might eventually drift close and merge, releasing a burst of gravitational waves. But these events will be uncommon and spaced out over enormous distances. Most black holes will be alone, slowly orbiting the galactic core or wandering through the emptiness. The dominant energy in the universe will be a faint bath of background radiation, leftovers from all the light that was ever emitted, stretched to longer wavelengths by the ongoing expansion of space. This radiation will be incredibly cold, just a whisper above absolute zero. It will no longer heat anything, no longer push or power anything. It will simply be there, filling the void. Over time spans even longer than 100 trillion years, the black holes themselves begin to disappear. This process of black hole evaporation is incredibly slow. A stellar mass black hole might take more than 10 to the power of 67 years to evaporate completely. A supermassive black hole at the heart of a galaxy might take 10 to the power of 100 years or more. But given enough time, even the biggest ones will vanish. They will shrink and shrink, glowing slightly hotter as they get smaller, until at the very end they give off one final burst of energy, and then nothing. What remains is an expanding universe filled with low-energy particles, faint radiation, and a flat geometry approaching maximum entropy. This far-future radiation will come from the evaporation itself. Brief flashes of light and particles that mark the final stages of these mysterious objects. Once those final flashes have faded, the universe will be left with little but photons, electrons, and neutrinos, drifting through space, too vast for them to interact meaningfully. The black hole era represents a bridge between the age of structure and the age of decay. It's a phase where the last major pieces of the cosmos still exert gravity, still hold together fragments of what used to be, and still mark their presence. But it's also the last time anything truly large or complex exists in the universe. After the black holes are gone, there are no longer any objects in the way we understand them. No stars, no planets, no clusters, just a thin mist of particles and fading energy, spread thin across an ever-growing space. Some theories suggest that long after even this, quantum effects may still cause fluctuations. In some versions of the far future, a new Big Bang could emerge from one of these fluctuations, starting another universe. Or perhaps time simply stretches forever, with no new beginning and no final collapse. But all these ideas lie far beyond what can be observed or tested with our current technology. No form of life we know could witness this era. It unfolds over timelines longer than biology can survive, longer than planets can hold together, longer than atoms may remain stable. And yet, the black hole era remains a part of the same universe we are living in now. The forces shaping it are the same forces at work today. In the deepest sense, the last light of the universe is already being written, just as surely as the first light was. And on that note, today's voyage comes to a close. What other topic would you like to hear about? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.